seats in the front occupied. That's okay. Whatever's more comfortable for you. Yeah, it's okay. Great. I hope there wasn't too much traffic on the way today. We'll just pull up this intro slides. Yeah, let's go on to the first slide. Yeah. So in terms of locations, right? So it's not just the customer facing locations that we are available in, which include Singapore, Malaysia, Indonesia, but also other R&D centers, which are similar to Bangalore that we are available in. We've impacted about 670 million people, and it just is growing every single day as we speak. And this is across geographies in Southeast Asia. And we're present in 400 plus cities. We've got about more than 214 million downloads and impacted 9 million plus partners. And this is growing as we speak every single day. We move on to the next slide, please. So Grab is truly a super app, right? In terms of food and delivery, mobility, fintech, all of the services that you see listed here. And there's a lot more that's going to come up as well. So you see Grab Food, Grab Taxi. So we started as a ride hailing service, then we moved on to food, then the fintech side of things. So there's a lot coming up as well. In terms of our mission, value, and proposition, right? Unlike a lot of them who just like to kind of go ahead, capture the whole space, we're all about sustainability, social empowerment, economic empowerment, financial empowerment, where we talk about enabling others who are financially lesser in the whole dimension, training our partners, right? So training our partners in the right way. So we have a lot of merchant partners, food delivery partners, ride hailing partners, diversity and inclusion. Truly as a company, we believe that Grab is committed to leaving no one behind while we are going economically forward, right? And our mantra is grab life with both hands. So it's not just about work, it's about work plus what you do outside of work, right? So that's what we stand for. Okay, so this is the last one. So we'll play it after this. So that's okay. So here you can just scan this. Just go back to that. Yeah. So you can just no the last one. Yeah. So this QR codes you can scan for going onto our Grab's careers website, talent community newsletter, as well as the open roles that are available in the Grab India R&D Center. Right. With that, I want to hand it over to Anshu.
Thanks, Kunmesh. Folks in the room, can you see me and hear me? All good?
1 second. Yeah. We'll just enable the side view. Hold on.
Maybe you can stop sharing the screen and then.
Yeah. Let's just stop sharing the screen. And then the view, we can change it. Yeah, Anshu, you're right.
Hey, folks. Okay, so hopefully now everyone can see me good and can hear me good. Okay, I'm assuming that's a yes. Otherwise, I'll rely on Anil, Kunmeet, and everyone else to give me a prompt on our usual and other channels. It's a first and foremost, I'm Anshu Prateek. I head SRE and databases for Grab, financial group specifically. A whole lot of my teammates are there in the room right now. I'm based out of Singapore as of now, working closely with the teams out here. Been part of LSP since early days. I was with Yahoo, and I definitely heard a whole bunch of familiar names. Hi, Roland. Hi, other folks. I think we also had Ramki in the room. So hi, everyone. Would I would love to be in person? Unfortunately, yes, didn't kind of line up with the times. We were supposed to do it earlier in the month, and then Bangalore rains happened, and then we know what all happened, especially on this stage of Outer Ring Road. Thankfully, our offices were all good, but yes, we definitely had troubles nearby, right? Before I get started, a huge shout out to everyone who has joined us this morning. Thanks to everyone for coming down to this place, and we'll keep doing this on a quarterly basis. This is 11th year for LSP. Thanks to Khunmir and everyone else, Alvin, and all who are there, who are helping us in this event today. Like I said, I've been part of LSP for about 10, 11 years now. This is the 11th year for LSP. What is LSP about, and why are we doing this, right? LSP in short stands for large scale production engineering. What exactly is large scale? It may mean different things to different people. We have talks from Twitter who are going to talk about millions of RPS per second, millions of tweets, and petabytes of data sets, right? So Twitter, for example, in context of this particular talk, they'll be talking about 3 trillion events per day, right? I'm not on a, if I have to make a guess as to how many zeros they are, I would love to see if I could have that many zeros in my bank account, but yeah, I'll live with that many events on my servers for the time being, right? Today, Abhishek and Soumya are going to talk about 3 trillion events per day, along with the SLOs and SLIs they have set up, capacity planning and performance optimization. That scale at one level, that could be huge for someone. That may be small as compared to a whole lot of other events as well at the same point of time. Why am I calling it huge and small at the same point of time? Simply because it's relative, right? No one big thing is big for anyone. On the other side, we have the closing talk is also the starting talk starts about Azure CDN, and in fact, sorry, that's another talk. This particular thing does talk about on-prem and Google Cloud at scale. At the same point of time, we have another talk from LinkedIn, which talks about how they were able to migrate over to Azure CDN, LinkedIn being a Microsoft company, how they're making use of another Azure front door CDN service, and how they were able to make use of it to ensure they have a performant and easily operatable service, right? Our closing talk is also from someone who has made use of Azure services and is ensuring that his service, quiz.nofab, is able to scale out, let's say, to 100,000 events, right? So now think of it like this. We have 100,000 users versus 1 trillion events. Both of them are 2 different scale of numbers and still are massively scalable in their own terms. So it's not one particular thing. It's not particular one number which defines as to when do you hit large scale. Grab, for example, does its 1 billionth ride sometime in 2017-18. So it took us about 5 years to do 1 billion rides, 1 billion transactions, versus we did our 10th billion transaction earlier this year on 4th of July, right? So 5 years for 1 billion, and from 1 billion to 10 billion in the next set of 5 years. I think we had hit our 2nd billion and 3rd billion over a matter of 12 months and 18 months, something like that. I don't remember that explicitly. Yeah, I'll check on that and come back. But yes, so the LSP large scale means different things for different people. The most important aspect is the common underlying term, the common underlying aspects, and how should we be looking at it. Over a period of time, when I started off working, it was about systems engineering, about sysops and such aspects, right? We had sysadmins and such titles in place, norms in place, which evolved to DevOps, which evolved to SRE, something which has started blowing up, at least on my LinkedIn feed over the last few days. Hey, is DevOps dead, right? Is platform engineering the next aspect, or is no ops the next aspect? The toolings, the nomenclature are one set of it. There is no one fixed thing that's gonna make it true throughout across the board. At Grab, or especially at GFG, at GrabFin, what we focus upon is what is it? How can we enable teams to deliver, right? It doesn't matter who's doing what, but rather how can we ensure that teams are able to do whatever is needed? For example, infrastructure as a code for us, what does it mean? It means that no one should be writing that Terraform code, right? It's not about making it self-serve. It's about ensuring whatever gets done without anyone having to do it. If there is any one thing that everyone has to do, let's say, be it infra creation, be it CI/CD pipelines, be it deployment, if there is something that everyone has to do, we work upon ensuring how do we get to that place where no one has to do it, right? Where it works seamlessly on its own and simply follows the signals, simply follows the patterns and get things done. Are we there yet? Partly, in bits and pieces. One goal that I have, that I kind of keep for my team, is how can my team, and my team is responsible for SRE and databases for whole of Grab Financial Group, right? How can my team be in Goa for a week without any firefights, right? For folks who do on calls, who have been on calls and have had the unfortunate pleasure of having a team outing or even a team lunch dinner while they are on call, right? I'm sure if they would have had to take their laptops and they would have to ensure that they have a redundant connection, if not their mobiles, then some other data cards, things like that, right? So from that place where an on-call has to be present and being available such that they are able to jump on quickly as and when needed, to a place where where the team could be in Goa for a week, hopefully without their on-call laptops. How do we get to that place? That place we could be in only when we have ensured that the weakest link is not there. What is the weakest link? Unfortunately, we are the weakest links, right? The machines will keep working. The systems will keep on doing. The biggest challenge to any system is a change, right? Go back and look at any incident across the board, be it a Twitter incident or a Google incident or a LinkedIn incident or a Grab incident. More often than not, an incident is triggered by a change. How can we ensure that changes are introduced in a safe manner where if something goes wrong, we do immediate rollbacks, we do blind rollbacks? It doesn't mean that such blind rollbacks will completely eliminate the challenges. In fact, one of the incidents we had recently internally, it wasn't a big incident, but it was enough that everyone had to jump on a call. And in fact, that particular the owners of that system were in fact in Goa at that point of time. But yeah, jokes apart, yeah, we were rolling out a change. We had auto heal systems in place. The auto heal system did detect that, hey, it looks like this change is not working out properly. The auto heal system started rolling it back, but still the change had rolled out enough that the rollback was not enough to auto heal it. Thankfully, it did not go all down. We were able to recover in time. We had enough people on the call and we identified what to do. But how do we get to that place where such changes could be rolled out in a safe manner, the same way as how an engineer is looking at it and observing the metrics and rolling it out to from that place where everyone signs off on it and says, hey, this change is good enough to be rolled out, the system and the changes get rolled out. How do we get to that place? That is the key aspect, be it via using SRE tools, be it via using DevOps tools, be it via using platform engineering, or be it via using NoOps tools, right? I'm sure everyone in the room, I hope everyone in the room exists, that we would strive to be in there. And I guess that's what everyone in the room strives to do, right? How can we get everything done without us being on call over the weekend, and where we can spend our weekends in such meetups or catching up with folks. I heard someone saying, I don't have a girlfriend, that's why I'm here. No, a whole lot of us definitely do have girlfriends who have been, who are lucky, or rather who have blessed us to be our wives and have blessed us with families and everything. And still we have a whole lot of folks in the room. So thank you everyone for taking time out from your families, from friends, girlfriends and wives and kids, and blessing us today with your time. And yeah, I hope it's a good utilization for everyone's time. Today is a packed event. We have 5 events back to back. So yeah, we would hope to evolve such events further. We hope to engage more of you. So yeah, if any one of you would like to present, do reach out to us. We have a Meetup group, we have Slack groups. That's where we engage. So yes, I'll be sharing again the Slack event where we participate and engage folks. Without further ado, I'll open the floor to our next presenter, Abhishek and Soumya from Twitter, talking about applying SRE principle to ingest 5 petabytes of data per day in a hybrid infrastructure. So Abhishek, over to you.
Thanks, Anso. Thanks for the great hint. So I would say. Are you sharing? Am I audible?
This is nice, right? I know as a matter of fact, I can see the screen and you all can see the screen. So this is something that is good when you do any events in person. Anyway, hi everyone. Thank you. In fact, LSP organizers for doing this, and shout out to all you folks for making it and mustering enough courage and interest. Oh yeah. Okay. Sorry. Okay. Okay. Yeah, now there is a trade-off between virtual and in-person event as well. So, okay. Sorry, anyways, shout out to all you folks for actually making it to a tech talk on a weekend. So we'll try to make it worthwhile and interesting for you. Having said that, today's talk is going to be how we at Twitter reliably ingest 5 petabytes of data per day in a hybrid infrastructure, which is both on-prem and cloud. In the next 30 to 40 minutes or so, we're going to focus on 2 main things. One is an overview of the architecture that we have to ingest data at scale, plus the replication system, both batch and real time. Also, just as a disclaimer, in the interest of time, we'll be focusing or mostly inclined towards the cloud infra and the cloud side of things. Yeah, sure. Or okay, on that note, going on with the introduction. Hi, everyone. I'm Abhishek. I work as the senior site reliability engineer at Twitter in the data platform team. I have like an overall experience of 6 years. And during my tenure, I worked mostly in the SRE or production engineering space with Yahoo and Walmart, and now at Twitter. I'll hand over mic to Soumya so that he can introduce themselves, then let's take back the mic.
Thank you, Abhishek. I'm Soumya. I work at Twitter as staff SRE for data platform team. I have around 13 years of experience. I have worked at SRE space. I have worked at systems engineering space, software development space. Yeah, so before Twitter, I was working at LinkedIn, as I said before. Yeah.
Okay, thank you, Soumya. Moving on. So let's take a look at what an event log pipeline is, right? So when you tweet, when you open Twitter on your app or web, whenever the user has any sort of interaction with the app or on the web page, it generates events, right? And these events flow through across data centers, just geographically located across different regions of the world, flow through Twitter's data centers, then into our pipeline, and which, based on the business need, they're grouped in the form of something called as events. Then again, these events are formed or grouped in the form of data sets. These data sets are then stored onto, ingested in certain way that we are looking at it, that the yellow box that you can see is what we're going to focus on today.
and ultimately get into the storage systems that we have so that our data engineers and data analysts can run ad hoc queries, or in fact, even near real-time queries. Moving on. This is the scale of our event log pipeline. We ingest about 3.5 to 5.3 trillion events per day with an uncompressed data size of like 20 petabytes. So now we'll start with the architecture of the batch pipeline from left to right. I mean, this is like 10,000 feet overview of what we actually handle and what we actually run. So from left to right, first is the client event layer. That is where all the events are captured. The user events interactions are captured, and based on the business needs, like they are tagged as to what log categories that, as we call it, or the event log categories as we call it, has to go. So this is running across various data centers and more than like 100K instances. Once these events are pushed into the into Twitter internal DCs called the real-time clusters that we have, we're talking a little about the Hadoop space, and it's aggregated via Flume. We use Apache Flume, which is an open source transportation layer in a nutshell. And there are close to 10K instances across DCs that run, and they aggregated based on certain time intervals defined by our pipeline. And once that events are aggregated, it needs to be processed. For example, you have to compress it, apply some sort of business logic, and other things, right? So the processing layer we've built is on top of Apache Tails. So it's sort of a DAG-based distributed processing framework that we have that in turn runs MapReduce jobs. And also we have that to kind of just denote the scale of jobs that we run. And the 10K jobs that you see, there are core production jobs only. They're not like ad hoc jobs or anything, right? And we run this across multiple data centers with a scale of like 60K nodes, which is across clusters. And each proc, or which we call it as processing clusters or production clusters, having like 10,000 to 12,000 nodes. This also includes the GCP, but we'll not talk, or maybe that warrants a different talk, maybe for some another day. Eventually, once these events are processed, they are pushed into the storage layer or the data warehouses that we call. It's either HDFS, Presto, Scalding, and even BigQuery. We'll talk about it in the next slides. So this was about batch. So if you go back into the slide, then we can see that if T is the timestamp when the events are generated, for the same event to be available after being bucketed based on the source time would be at least T+2. Because after processing, we also do some replication across clusters, etc. So if so that would be like close to 2 hours for the events for events to be available to run any sort of analysis. So this was something that we wanted to do away with. We wanted to try and enable and try to find possibilities if we can actually enable and facilitate near real-time querying. So hence the idea. So as I mentioned, so we wanted to reduce the end-to-end latency in terms of minutes or even to seconds based on the dataset size. Then the data storage the insertion in data storage has to be near real time. That's when you can run the query near real time. So looking at that architecture now, moving on to the next slide. Yeah, so this is the streaming architecture. In a nutshell, it's going to be the event layer, the client's layer is going to remain the same. We run a daemon. It's an inbuilt in-house daemon that we run on Twitter across all microservices and mesos, etc. Mesos instances. And then they're pushed into the streaming aggregation. Up until the real-time cluster is going to remain the same, but from Flume onwards, we don't have a processing on. We don't leverage Tails. That would be mostly for the batch. So what we do is ultimately we want the data to be in BigQuery, and we are big on GCP, right? We're big on GCP, and the way we currently push and stream data in real time to BigQuery and GCS is leveraging PubSub. So you push events from coming in and aggregated from after Flume aggregates it, push it to Google PubSub, And from PubSub, we have Apache. We leverage Dataflow, which is managed, which is managed processing jobs that we processing framework that we have that underneath leverages Beam SDKs. So that would pull the events. We use streaming pull from PubSub and underneath pull these events and push it into BigQuery in near real time, leveraging the APIs. So this is like, in fact, like a 10,000 feet overview of what happens, but we'll look at a better architecture. So the same thing, but kind of has more components that is easy to understand. So these are the microservices pushing events, and this is the Hadoop real-time clusters. Yeah, so this is going to just aggregate. We're not going to process anything here. Aggregate, and over a private interconnect, we push it to PubSub, and each of these log events are mapped to one single topic, and each of these topics have multiple subscriptions based on what is pulling it. It's based on like there's one subscription for BigQuery, there's one subscription for cloud storage. The Dataflow jobs are orchestrated via Airflow scheduler, so it automatically picks up all the changes. So we're completely hands-off things here. Nobody handles and like goes and does does manual handling of these pipelines or management of these pipelines. It's pretty much automated. So the scheduler picks up, notices the change, pulls it from the required topic with already created subscription, and in case the user want some sort of transformations to happen, that can be defined again. Yeah, that is already defined because that data flow loads a jar, and that is a custom Hadoop, the Twitter Hadoop or the Twitter jar that we have that's leveraged for processing, and then pushes it into BigQuery and GCS. So this is the streaming architecture in a nutshell. Moving on, so what did we achieve with this, right? The end-to-end latency that I previously mentioned was in the order of hours, in fact, at least 2 hours. But with this, and we internally call it Sparrow because why not, right? A bird name is something we fancy. And yeah, the results seem very promising, and you can see the kind of latency that we have reduced from the order of hours in the order of seconds. So for very small data sets, it's like in the order of GBs, would be like approximately 0.5 seconds, ranging from GBs to terabytes of data, which would be the data set 4, would be like less than 10 minutes. So this is what we've achieved, but how were we able to achieve this reliably, and how were we able to scale this? And this is where the SRE principles come in. So we work very closely with the developers of any platform and any product or any service that we work. And we ensure that to make this possible and to make these production changes as smooth and as seamless as possible. So we had this is one of the things that we did because like we thought let's pick just one case study and talk about it. So pretty much we needed a staging environment that would mirror the production environment. So we cannot make changes in production because they're all revenue impacting and very critical. So pretty much all of our infra on cloud is set up leveraging infrastructure as code Terraform. And we ensured that the staging environment mirrors production. So what we did is whenever a developer makes any changes to the code or any configs for that matter, there's our CI jobs that actually get triggered on these changes automatically, and they push it to the Google Cloud Storage staging bucket. So we have this environment is completely isolated from production, right? And then there is the GKE Google, which is on Kubernetes, Kubernetes engine, staging Airflow scheduler that kind of schedules and triggers these jobs. So I already spoke about a couple of subscriptions that we have. So one, we have a production BigQuery subscription and one for GCS. So we have 2 more for test, like test subscription for each one for the destination, which is BQ, BigQuery, and GCS. So those tests, the data flow job runs and they pull data from the test subscription. We want to be sure because we want to pull the same data as well, right? We don't want to just test it on some random data because the kind of data formats are also different based on what team it is and etc., based on the customer demand. And ultimately, you push it to the staging GCS destination and BigQuery. I'm not going to talk about how we set up monitoring, alerting. This maybe that warrants a different talk altogether. But this is, in a nutshell, this is what we have tried to achieve. So this has helped and facilitated better developer velocity, as a matter of fact, and also has sort of given the confidence to push changes very often. I just want to touch upon like another, in fact, caveat with the initial architecture that we looked at. Due to some organizational policies, and there's something called as demigod. Maybe I can share the talk later. So that kind of sets up all the service accounts, etc., with all the right permissions and all these things. So that sort of limited the creation of service accounts in one particular GCP project. So what happens with PubSub, unlike other resources, PubSub quota is basically connected to the service account, not the GCP project in where you're running it. So we kind of figured this out, and we did not figure it out just like that. So we actually ran into production issues, like we were not able to consume more data, and we saw quota limits. And when we checked on the GCP projects trying to push data, or even like the one that's trying to pull, the quota were looking fine. We were trying to figure out, hey, where is this quota being utilized, right? Then is when we figured out that the PubSub quotas were shared across all, of course, like all PubSub accounts. And because of that, we were hitting quota limits, and that was affecting the availability of Sparrow, or the real-time event log pipeline. So that was a good find that we had, and we ensured that we break that sort of organizational policy we have, and then created different service accounts on the processing GCP project where we run data flow jobs. Now, this way we completely isolated the problem that we had with running into quota issues and shared quota, and that way kind of solved noisy neighbor problems that we're having. So this was about the event log pipeline and how we're trying to make it more reliable, available. Now, I will hand over the mic to Swamideep, who's going to talk more about the next gen replication system and the frameworks that we have implemented in the SRE team to make it more scalable and available and robust. Over to you, Swamideep.
Thank you so much, Abhishek. So taking forward, this diagram kind of represents our data replication pipeline. It has the stream ingestion pipeline in one hand, we call Sparrow internally, and then we have data lifecycle manager, the batch ingestion pipeline that we have on the other side. So with batch ingestion, we replicate data from HDFS to GCS. GCS is Google Cloud Storage. And as well as BigQuery, and Manhattan is Twitter internal key value store. So not going into the details of architecture of the batch replication system, but I just wanted to share and show the complexity of the service that we worked with and why it warranted us to invest time to make it, to ensure reliability as it was being developed. So just to give an idea about how it works, so we have a metadata system that's called data abstraction layer. Internally, it's called DAL. That handles all of the state transitions of, like basically trigger for replication. So we get indication of whether or not to replicate data from one, let's say from GCS, Google Cloud Storage System to HDFS or not, or from GCS to BigQuery or not, using this metadata system, which has the state transitions, right? And then the events flow through to something called event generator. That's within the ecosystem of data replication service. So that creates work for the coordinator, which is sort of like a job scheduler, and also keeps track of the progress of job. Right. And then we invoke, we actually use the workers to invoke data copy jobs, and data copy jobs could be DCP jobs to copy data from HDFS to GCS, or data flow jobs to copy data from GCS to BigQuery. So this is sort of like on a very high level without going into the details of the implementation. So let's see how we sort of brought in more reliability into this complex system, right? And why. First, we wanted to see where we can, what we can do in terms of integration testing, right? As we saw, this is a very complex replication system. We have a bunch of services, both internal and in GCP. We have to ensure that they talk to each other and the whole thing actually works the way we expect, right? We have to test all the metadata transitions as well. We also want to ensure that the tests are performed before every releases religiously, right? And we also introduced something called dry run, so that using that dry run, we don't have to wait for data copy to be completed. Rather than that, we will only test whether the data copy job will be invoked or not. Also, there's something called schema test. We wanted to ensure that, so basically Twitter uses Sparky as data format, mostly 90% of the time. And when we are ingesting to BigQuery, BigQuery supports Avro. So we have to ensure that the schema tests actually tests that the deserialization and reserialization to Avro does not break. Let's go into the next one. Okay, so this is sort of like a high-level overview of how the functional test or integration test is performed. We use Aurora workflows. Aurora is built on top of Mesos, but it has very good integration with Kubernetes as well. Aurora workflows is the de facto CD part of infrastructure at Twitter. We use Aurora workflows to run the integration test. So it creates artifacts, the jars and pexes, and then we deploy services in the Devil instances. Then we run the functional tests or integration test. And if any of the tests fail, developer gets a Jira ticket created. We are also in the process of integrating with Fabricator. We use Fabricator for reviews, code reviews. So what happens in that case is that whenever a developer raises a code review, a significant portion of the code review, this entire pipeline is triggered, including integration or functional test, so that developer gets an opportunity into look into the issues if there's any early enough before it's even merged to, let's say, master. There's another very important aspect of testing is stress testing. So functional test is going to test whether all of the pieces talk to each other the way you expect or not. But if you're working with many pieces, especially cloud, and then you also have on-prem thrown into the mix, you do need to have stress test. We didn't have much idea when we gotten started with this service. We didn't have much idea about the scalability of data flow or BigQuery ingestion. We needed to perform stress tests to understand those pieces better. So why we need to perform stress test? We want to understand performance bottlenecks. We want to understand how during the severe stress, whether there's any upper threshold that can cause breach of SLO. SLO, we'll talk about that later, few slides later, but SLO in this case is the end-to-end latency. And also we have to understand the resource consumption of each of the system, right? So data flow, GCS, BigQuery, SDFS, all of that. That helps better capacity planning. Okay, this is a case study. This is what we performed during stress test. We wanted to ingest XTB data into BigQuery using data flow job, hundreds of parallel data copy jobs periodically for X hours, and then capture end-to-end latency. And then in every iteration, we wanted to increase the data copy size. Once again, we used Aurora workflows as it's the de facto CD infrastructure. And the Aurora workflow will build jars or prexes. It's going to invoke the copy job workers. And then the metrics are automatically published in our observability infrastructure for us to analyze later on, what are the sort of like highlights of stress test. We also want to integrate, we are in the process of integration so that we can stop the whole stress test when a certain pre-configured threshold is exceeded, right? So that we don't want to run the stress test until everything breaks apart, right? Let's go to the next slide. Okay, so this is sort of like important finding we found. So we ran sort of like 30 parallel copy jobs, each with 1 TB data, and test duration was 8 hours. We were able to copy using data flow, like during the stress test run, like within 51 minutes, we could actually copy 1 TB data to BigQuery using data flow jobs. Also during the time, BigQuery slot usage was about like 21,000. Yep. So in terms of monitoring, this is the real kind of picture from the dashboard. I don't know if if it is visible, but basically it gives an overview of it gives an overview of all the things that are related to replication, be it end-to-end latency, how we are doing in terms of SLO, and also from the customer point of view, customers are usually data engineers that have their data pipelines, etc., dependent on the replication system. They can, from their point of view, they can see how per each data set the replication is happening or not, whether there's any lag, whether there's any delay, whether there's any failure or not, and also we alert in case of failures. SLO, very important thing. We wanted to ensure, even though this is internal service, we wanted to ensure that we understand the customer, the need of the customer, and we provide the best we can with the capacity and cost, right? So that meant we implemented SLOs. We have like 3 tiers, and every tier has a definite latency expectation. In this case, the SLI is end-to-end replication latency, right? And we calculate error budget at 95th percentile, which means that like 5 is the error budget, 5% is the error budget. In the graph, we can see how we are doing in terms of error budget, right? How much of error budget we have left, right? So in this case, we see there was some replication failures that brought down the error budget utilization to 95, around 95. So if it goes down below 70%, we have to freeze any further production rollout and have to see how we can fix things, whether that means capacity uplift, and it can be anything else as well. Okay, so capacity planning, how we sort of devised capacity planning. So we ran stress test, we did sampling of copy jobs, and we also applied regression because, as I told in the beginning, we didn't have much idea about what were the relationship between an input data size and the data flow workers or even BigQuery slots. We had to get to that by all these 3 methods using stress test results, sampling, manual sampling of copy jobs, and as well as regression to feed the data. And this is once again a real snapshot of what we have. We have a data studio dashboard that can calculate and tell you that how much data flow, how many data flow workers you would need and how many BigQuery slots you would need given an input data size. All right, these are the few takeaways during the capacity planning or what we learned from the entire exercise. Data flow, copy job, resource utilization, it can vary widely depending on the data format, various data format, the kind of compression that goes into the like in input and output data, as well as data load API. So ingestion into BigQuery API has 2 different kinds of API. And when you try to ingest the same data using both the APIs, there's a huge variation in the test result. We also, another learning is that like build capacity and cost models, especially in case of cloud, build capacity and cost models as early as possible. So that that gives insights into the capacity or utilization expectation and the cost for the components, right? We saw some opportunities to optimize like, for an example, ingestion from GCS to BigQuery can happen without even data flow. Google provides that. All right, so that brings me to the end of the presentation. We talked about, mostly we talked about cloud. We want to talk about on-prem, but that calls for another talk at LSP probably next year. Thank you so much for giving us the opportunity and time to present about what we did from Data Platform. Thank you.
Can we open up the session or flow for questions, or we're going to come back? Yeah, I think we can. If there are any questions, we'll be happy to take it. Yeah. I think we have a question.
See, one slide shows like P5, P95, and P99 budget, right?
Yeah.
Oh, like previous.
Is this the one?
No, where you show the metrics of all the.
Oh, the latencies? Are you talking about this?
Yeah. So what are the parameters you take consideration while you calculating all this thing?
Okay, so let's get into this. So to explain this, I'll need probably this. So PubSub insertion timestamp is something we consider because that's when we push the data into, that's when the data arrives into PubSub, and this would be like negligible because you're continuously streaming it. From there, then we during when we insert it into BigQuery, we actually have like a BigQuery insertion timestamp. We take a delta of it, and that's how we get that. Once we get those metrics, we plot it and take a P95 of it. Yeah. Is the question answered?
No, you measure this. This is a parameter, but how you plot that? Can you grab it? Can you show? Like your rate. See, go to the next matrix.
Okay.
It is drastically decreasing, right?
Drastically decreasing in terms of
the latency timing.
So
what you did?
Is it decreasing or is it increasing from left to right? Right, P90 to P99.
It's decreasing, right?
It's increasing left to right, right? P90 to P99. So it's 6.3 minutes. P99 would take more time, which is like 7 minutes.
It is increasing then?
Yeah, that depends on the data sets that we have. So it depends on the kind of data sets we like. So P90 would be like 90%, approximately 90% of the data sets, right? But P99 would be like 99% of the data sets. So there might be some outlier data sets. And that's the reason we take percentile and not averages, right? That's the reason percentiles is a better measure of this. And yeah. Okay, thank you for the question. That's a good question. Yeah, I think we have another gentleman here.
So I just checked that Aurora is being retired officially.
Yeah.
Do you also have plans to move away from Aurora to something else, or do you plan to maintain it yourself?
So we are currently actually maintaining it ourselves. Like we have a lot of, so basically that is true. The point is it's not under active development for sure, but it's not like deprecated at Twitter. Like we use it heavily because it works very well with Apache Mesos. We are not completely on Kubernetes. So we are in that transition. So at least as long as we have Mesos, and until then we'll have Aurora internally. And it works like a charm for our infrastructure with Mesos especially. Yeah.
You have one question.
Hi.
One
quick question here. You mentioned about independent pipelines. So is it a group of pipelines you manage for the E2E validation, or is it a single streamlined pipeline?
No, it'll be group, right? Because of multiple data sets.
Yeah.
Yeah. So it'll be group of data sets. Yeah.
Thanks.
Any other questions? We're good.
Okay, thank you.
Thank you. So thanks, Abhishek and Samadhi, for this wonderful and interesting talk on the event ingestion. So next, I would like to invite Yogesh for the next piece of talk. Yogesh.
We can take a 5-minute break for quick tea, coffee, boss rooms till the time we are setting. Till the time our next speaker is ready, we can grab tea, coffee. Thanks, folks. So we have 1 more minute. Let's settle down. Hey, folks. Time check. Let's start back. Let's just start back. Time to restart. So we are starting in 1 minute.
Hello.
Thanks, everyone. So our next speaker is already on the deck. Over to you, Yogesh.
Hello. Hello, everyone. So I'm Yogesh. I'm part of Edge Engineering at LinkedIn. What we do basically is we make sure that whenever you try to access linkedin.com, we make sure that your request reaches our data centers, right? So we basically act on the internet once it reaches the data centers, then our job is done, right? So the team that I'm part of, they basically act on the internet stuff for linkedin.com, right? Today, so we in general manage the entire traffic layer of linkedin.com. So like how basically it reaches to our data centers plus CDNs. So we have a bunch of CDNs basically across the globe. We also manage the steering part of it, right? So how you route the traffic using DNS and multiple other things, right? So LinkedIn at the moment has presence in more than 200 countries with over 850 million users actively using linkedin.com at any point of time. So before we start, the agenda looks like this. So we are going to talk about how the LinkedIn CDN architecture look like, why we tried migrating from one of the previous version of Microsoft offering to the newer version of AFDX, the strategy that we followed, infrastructure code, bugs and challenges that we found and contributed back to Microsoft, right? The improvements and the open source contribution which you have made as a part of this strategy migration. So before we start, right? So LinkedIn at the moment we are having 5 CDNs, right? So we don't rely on one CDN because we believe that one is not an option, right? So we have 5 CDNs and our content on the CDN is being divided into 4 parts. So these are known as static, platform, media, and DMS, right? So static is basically all LinkedIn generated content like CSS, JavaScript, right? platform is again LinkedIn generated CSS content, but they are being also integrated by vendors. For example, Microsoft Office, it integrates with LinkedIn in some way, right? So they use our platform property to integrate with that. Some other vendors, maybe like for LinkedIn Learning, there are many other vendors which uses for it, right? Media property is basically what member uploads. So when you upload your profile picture, your resume, or anything, right, it is being categorized as a media property on LinkedIn.com. And DMS is nothing but video, right? So when you upload a video or you see a video on LinkedInLearning.com or anywhere on LinkedIn products, right? So we categorize them as a DMS, also known as video on demand, right? So at present, we have 5 CDNs, out of which Akamai, Edgecast, also known as Yahoo CDN, and Microsoft CDN. This serves our global members, which means everyone out there except China, right? In China specifically, because of compliance thing, we have Akamai, Contil, and Alibaba Cloud, right? So in China specifically, these 3 CDNs are there, and in global, we have Akamai, Edgecast, and Microsoft. So this talk is specifically, we are not going to talk about China, not talking about Edgecast and Akamai, but mainly into why we move from Microsoft CDN to the other offering of Microsoft CDN, right? So before we start, right, so Akamai and Edgecast, right, at any point of time serves all these properties. So they serve static, platform, media, and DMS. But Microsoft CDN can only serve static and platform. So we have not onboarded media and DMS onto it, right? And there was a reason for it, which we'll come and discuss, right? Why we have not onboarded media and DMS, which is kind of doing a heavy lifting for entire LinkedIn traffic, right? So if you see, right, I mean, I think it's not visible. So if you see, for example, right, I mean, if I go for static, right, I'll just go little interactive here. So these are the static properties which is generated by LinkedIn, as I mentioned. So you can see these are our JavaScripts and CSS. Same way, we have media, which is basically is being generated by some of you. So if, for example, if we see, right, this might be someone's profile image, right? Similarly, we have DMS, which are nothing but videos, right? So for example, someone has uploaded some videos, which is being served over here. So this is how the properties is being divided. Before we move, like why we did a migration, this is the simple CDN architecture looks like in journal. So you have a browser, let's say any of the browser. You try to open a website called, let's say, example.com. The server responds the request. Then within the first request which comes in, right, it has certain, it has some data which tell browser to open further request, right? For example, to CDN architecture. So in general, it looks like this. If it's a hit, it's served from the CDN, otherwise goes to the origin and then being served, right? It's a single CDN architecture, which is mostly being used, but we decided to have a multi-CDN architecture in active way, right? So this is how LinkedIn CDN architecture looks like. So what happens, right, when you try to access LinkedIn.com, the very first request comes to us in our data center, right? We respond with LinkedIn.com being returned. Then that page which is being written, it has certain beacons, right? Those beacons will contain informations, and it has a tags to tell browser that you have to go to this particular CDN to download further request, right? But what happens there, right? It doesn't go to CDN directly. So what is happening? The browser basically redirects to one of the intelligent DNS manager called as Sedaxis, where it basically checks which is the best performing CDN for this particular user. For example, if someone's trying to access from Bangalore, Akamai might be the best performing CDN. But if someone trying to access from Delhi or let's say some part of the world, Akamai might not be best performing CDN for that, right? So to give a better better user experience to everyone, we decided to go multi-CDN, right? So Akamai is not doing well in all part of the world, right? Similarly, Yahoo or any other CDN, I mean, they have some gaps somewhere in the world where they don't have a pop locations, right? And that is where we decided to make this decision to go multi-CDN and decides based on user proximity, like what is the best performing CDN for them, right? So that's where the Sedaxis come to the picture. So browser, when gets the first page request, it goes to the Sedaxis, checks what is the best performing CDN based on time metrics. We have like availability of the CDN plus what is the response time, bandwidth, and other things, right? Based on that, that response will be cached on for some amount of time on the browser side, and then it goes to CDN, which is basically this part you see, right? So if it is a hit, it returns from the CDN, otherwise it goes to the LinkedIn origin. So why we moved, right? So basically, as I mentioned, right, we were not onboarded DMS and media property to what we called previous version of MicroCDN. So for this particular talk, we'll call them classic CDN so that we don't get confused versus AFD CDN, right? So classic CDN is the previous version of MicroCDN, which is still live. There are organizations which are still using it, but AFDX is a newer version of it. So Microsoft in 2022, they made a GA of AFDX saying that no further feature request will be made to the classic version of Microsoft CDN because they want to invest into this, right? It will be supported, it will have bug fixes, but no feature request, right? So when we had this news from it, one thing which was sure for us that new feature is not coming to us, and to onboard DMS and media, right? The first two things that you see over here, client to CDN signing and CDN to origin signing is important. Because of the GDPR compliance, you cannot have your content. Hello? So you cannot have your content being served on plain text. It has to be encrypted in a certain way. That point of time, I mean, still client to CDN and CDN to origin signing is not available, but it has been committed that Microsoft is going to provide these two features into the FDX, but not into the Microsoft CDN. Other important factor is negative caching, right? What if a bad user tried to hit our CDN infrastructure with random URLs, right? What happens with Microsoft CDN, right? It doesn't cache that. So anyone can do a cache busting attack, which means you can basically tell CDN to skip it and send request to the origin, which can literally overload your origins, and it can also bring down. So negative cache, if not implemented, basically generates a cache busting attack, right? So this was not available. The second part, which is the fourth option that you see, cache by origin key, which is not really a blocker, but it's kind of a performance improvement. So what happens if, let's say, you have a domain called 1.example.com pointing to your origin, and then 2.example.com also pointing to the same origin. What happens in current architecture, in classic CDN, they create two cache keys at the backend, and is being stored in a different cache location, for example, I'm saying. So what happens if 1.example.com is being serving a request, it has a hit, right? But if someone trying to access the same object with 2.example.com, it will get a miss, right? Which should not be the case. It should be by the origin key, not by the client side host that they are serving, right? And last but not the least, the byte range support, right? So when you are using a media, right, for example, video content, you don't want to serve 1 GB of video in one go. Like we use YouTube, we use LinkedIn Learning, right? So it has to be streamed in a way. So client will say that you give me a content of, let's say, from 0 byte to 100 byte, right? And then once it's been streamed, I'll take the other byte, and then likewise, I'll do the streaming for it. This byte range support is not available. It's now available. Last week it has gone GA, but when we did a migration, it was not available, and that was the blocker. You cannot serve a video content until it doesn't have a byte range support. You don't want to choke your network for downloading the 1 GB and ask user to wait for it, right? So we at LinkedIn Edge Engineering, we directly work with Azure Engineering to tell them like what is required and how we can basically move ahead from it. So the first two things, they has been qualified for coming GA soon, and they are going to use something called as function on edge, right? So Azure has something called as Azure Functions. As of now, it is not available on edge. It's a region-specific service, but now it is going GA, where it will be available on the edge. So people who wants to have an authentication between CDN to origin, they can write their own custom logic on function, and that will be taken care of it. And yeah, so all this will be available to all the customers, not just to the LinkedIn. We are part of Microsoft, but again, this will go GA for all the customers that Microsoft has. Right? So yeah, we'll come to the migration strategy, right? So we know now why we try to. So we onboarded classic CDN or Microsoft CDN, I think 2-3 years before. So we raise those features, right? But see, we raise, so initially if you go, I go back, right? So we raise, so client to CDN, right? Or CDN to origin. So we raise a feature of, we use AWS V4 algorithm for doing a signing, right? So we asked them to implement that, but because of other priorities and all, and we were having an option, Akamai, Edgecast, Alibaba, Contil, right? It was not prioritized in a way that it's not a blocker for us serving our members, right? We already have 4 CDN being serving our content. For example, if we say that we have to decommission everything else, then move to it, then it might get prioritized. But now with AFDX coming in, it's being prioritized. Okay, so migration strategy, right? I mean,
apology, we will taking the question at the end. So if you can hold, please hold at the end. Thank you.
So we highly rely on RUM, which is real user monitoring. So for Edge, right, which is not part of your data center, like it's on the internet, you need to rely on RUM data, which is real user monitoring, as in like where user sits, right, which ISP it uses, what is the bandwidth they have, how they connect to the LinkedIn Edge locations, which is POP. And based on that, so we started gathering YUM data. We gather it 24/7. And based on that, Sedexis make a decision, but we gather it specifically for the new offering called AFDX, right? So we, in our platform, we got an URL, or we did a test, basically created a test profile, started gathering YUM data. Based on that YUM data, we need to have 4 important metrics for serving a CDN, which is availability, right? So it should not be like, okay, so it's faster, but it's going down very frequently, right? So availability has to be up, at least 3 nines or 4 nines is required to move to that new CDN offering. We highly put focus on P70 and P90. A reason of not going to P95, P90, because in CDN world, you may have cache miss, right? When you have a cache miss, your percentile will go up, right? I mean, because it has to go to origin, come back, and you don't have origin across the world. It will be somewhere in your data center, which are very limited, right? I mean, it's not like POP location. So P70 and P90 is the thing. And bandwidth. Bandwidth is always required to serve your video contents, right? So these are the key KPIs which we have, which we started monitoring, and I'll show you live like how we did that, right? Then we went for, for a scalable ISC solution. We'll talk about this also. How we did a testing for it, then ramping strategy. I mean, even if it's a new CDN, it's being used by thousands of users. But when you onboard for your own project, your own company, you want to test it, right? You don't want to believe on other words and then decide to ramp it. So the ramping strategy and at the end, single CDN test, are also known as stress test, right? So before we go to the KPIs, right? So how we gather this RUM data and KPI. So we use a platform called Sedexis, as I mentioned, and Sedexis help us gather this RUM data. So how it works, so in LinkedIn.com page, whenever it loads, it basically it makes an API call to Sedexis, gathering certain data, as in like the geographical location of the user, what bandwidth they have, plus certain other time metrics. This data come to us, then Sedexis make that decision, right? Okay, for example, for a user coming from, let's say Delhi, right? They have, especially ISP, for example, Airtel network, right? They have this bandwidth, okay, this CDN might performing well. So what happens? The monitoring happens from the browser side. So LinkedIn.com loads, Sedexis gathers the data, it make a hit to all these endpoints, let's say Azure, Akamai, and other CDNs. It gathers the data, like what is the availability, P90, P95, and sends to the center platform, right? Which basically looks like this, right? So if you see here, right, before we did a migration, right? So this green line is nothing but Azure, right? So when I say Azure, it includes both classic and AFDX. So this is a date we did migration. Before that, Azure P90 was somewhere close to 200 milliseconds, right? For some, it's still faster, but you always, basically, when you are working on ads, you always want to gain that extra millisecond to serve your content faster. Because in ad world, in any world, that 1 millisecond is highly important, right? So after this migration, if you see, right, I mean, Akamai is still the best performing one at the 100 millisecond latency. Edgecast, which is Yahoo CDN, right? I mean, it was somewhere better than Microsoft CDN at that point of time. So we were having around 200 millisecond of P90, where Edgecast, which is Yahoo, was having 122 millisecond. After this migration, somewhere down here, you can see Microsoft is between Akamai and Edgecast. So that's how we do the monitoring, and we decides like which content to be served. So this is a geography. This is like global thing, right? You can get it from continent, country, region, state, network like Airtel, whatever, right? So all the granular data will be available to you. So now, I mean, I'm showing you just in general because that will take times to load all the data. But in general, if you see, as of now, Edgecast P75, 76, or P for Azure is 79. But if you go to P95, Azure is basically winning the race over there, right? So this is the platform that we use for gathering this data, which is also known as your RAM data. We'll come back to this, but we'll move to the ISE, right? So when we think about this migration, we don't want it to do a lift and shift, right? Which is like just put the things from here to there. So we want to visit our bottlenecks, right? So earlier we were using ARM templates, which is a JSON, and the number of rules we have, it makes the JSON almost like 2,500 line of code, which is not easy to manage, right? For example, I can write it, but if I want someone else to read it, it's not easy to read the JSON. You can't even put the comments over there, right? So we decided to scrap ARM templates and wanted to use some scalable solution. And then we started comparison, which is basically over here, right? So we picked some of the favorite or most used community supported one, Terraform, Pulumi, and Bicep. So based on, so we wanted to have certain features being supported. One, it should have a modular, right? Which is basically over here. Then it should have Azure managed state, easy to develop and maintain so that it has an IDE support. You don't need to remember syntaxes. If you have an IDE like VS Code or something, you can easily write it. Any new feature released to Azure should be available on the day 0. It should have Microsoft managed SLA, which means if something goes bad, we can ping them and they come online to help us, right? Either DSL or GPL, we are good with both, right? Should be open source. We don't want to invest money on that. And then it should support all the SKUs, right? So if people are using Azure, they know that what are SKUs, right? SKUs are nothing but different offering of same product, right? For example, a premium, classic, standard, and likewise, right? So premium is higher, classic, you get certain less feature, and likewise. So Terraform was ruled out in the very first state because it doesn't have a managed state. It basically stores a state into the in your bucket or in a thing. And based on the experience, it's very hard to manage Terraform if something goes bad the state file, right? With version 1.0 and plus, they have a backward compatibility, but previous version when we were using in a previous organization, it's very hard to manage them. So the very first block, it was the first blocker. Second blocker, it doesn't support day 0 support. If Azure or Microsoft release a feature today, it's not available into the Terraform in the very first day, because someone from the community has to write it, push it, test it, and then it will be available, right? It's not managed by Microsoft itself, right? Pulumi, it was one of the best choice because it is a developer friendly. You don't need to remember like your DSL language. You can write in your programming language like Python, JavaScript, TypeScript, whatever you want. Easy to orchestrate, things looked at. We can go with everything, but again, it failed on something called as Azure managed state. Backend, Pulumi also used Terraform CDK, which basically when you run Pulumi, apply and all, it basically do the same thing. And we don't want to go in the business of managing those state files, right? So we decided to go with a Bicep. Bicep is again an Azure offering. It's very in the early stages. I think not even first version of it being released. And it supports all those things for Azure. At least if you're using Azure, Bicep is a good choice. So modularization, Azure managed state. So internally, it uses Azure deployments, right? So Azure deployments are another offering which basically implement ARM APIs, right? So only thing is, it's not a general programming language, which is fine. Like Terraform is a DSL, so which is good. I mean, easy to learn. You can use, it has a VS Code extension so that you can write it easily without learning it too much, right? And documentation is very good. So that was the reason we adopted Bicep and we started writing to it, right? So while doing all this migration, right? Of course, everyone has tested out their product, but when we started migrating it, we found certain bugs in the front door, right, itself, which was very, so these are the core bugs that we found out. So very first is compression on fly. So when you serve content on CDN to your client, right, you don't want it to be in plate, it should be ggzip, either Brotli, zzip, or any sort of compression should be there, right? What was happening over here when you So there is a rule called route config override in AFDX, which means if I say /ABC should be routed to /XYZ, so once you apply this rule, what is happening? Compression on fly was stopped working. So we found out the bug with Azure engineering. They have fixed it. What was the bug? I cannot discuss it here, but it was a bug which has been fixed as a part of the release which has happened last month. Portal purge cache issue. So if you basically try to purge a cache with API, you don't need to specify a domain name. For example, abc.example.com/abc. You want to purge /abc, right? So what happens when you do it from API? You don't need to specify a domain name. You can say purge a/abc on this CDN, right? And it will purge it. But when you do it from portal, it was asking mandatory to select your domain, right? Which is kind of should not be there. And it's not a blocker for us. As I mentioned, we use management APIs. We don't rely on portal things. Second, if you disable something, you cannot enable it. It was a bug which has been fixed. We don't rely on it because we use management API. And likewise, the last one, which is interesting, which is what if issue. So if people are using Azure, they know when you do deployments like Azure group create, there's a provider called what if, right? Which basically tell you what is the difference between, it's like Terraform, when you do Terraform plan, right? It shows the difference between what is being deployed versus what is being not deployed. Similarly, they call it what if, right? So when you say what if, it shows the difference between what is being deployed versus not deployed. So what there's a bug when you use keyword certificate, right? So there's a property called use latest. So you say I'm always willing to use latest certificate version from keyword. What happens in that case? It will say, for example, let's say at today the version is 1. Tomorrow, because of you added a SAN or you changed the domain name, something like that, the version will move to 2. But it will always show you an issue that okay, this version is not matching your config. So this is a false positive. We have reported it to Azure. It's openly you basically, so this being available over here is being tracked by what if team, but by provider team, and is being worked at the moment. So these are the bugs we had. One thing which I've not listed down here, the challenge, right? So the previous version of CDN, classic CDN, they use something called as CNAME-based verification. So Microsoft will provide you their own version of domain name, for example, example.azure.afdcdn.net, something like that, right? You will not serve content from it. You need to have your own domain, let's say cdn.yourorganization.com, right? So in the previous version, they used to do this verification using what we called CNAME based. So you create a CNAME, they do a verification, and they will say, okay, we'll serve the content from this domain. When we migrated it, the problem is like over here. I mean, you cannot in Azure. It's a feature, or not a feature. It's a, you can say, a kind of a check that you cannot add same custom domain to 2 different resources. For example, if your domain is, let's say, static.linkedin.com, which is being used by one of the offering already serving a production traffic, and you're trying to migrate to a new CDN offering, which is AFDX, you cannot move this domain from here to here. What way you can do, you have to delete it first. The moment you delete it, you have an outage, right? Because you have to first delete it, and then you have to add it over here. So what is the way of doing that? And that's where the Sidexis helped us, right? So we told Sidexis, you take Azure CDN out of the traffic, whether it's best performing or not performing, do not send traffic for this property on Azure CDN. So when we drain out the traffic from it, and so it does automatically, but you can also tell that particular Sidexis that you have to do like this, right? So we told Sidexis that, okay, don't send traffic to classic CDN, and we want to do a migration, and we did the migration. Now in the newer version of FDX, they realized this issue that CNAME-based verification should not be there, and they have moved to something called text-based verification. So now you add a text record into your DNS, and now you can serve, basically the custom record will be added over there. Okay. So while doing this all migration, right, we got a good performance, right? So I showed you only the latency numbers, right, which we had. I think it's not visible over here. So we got like almost 50% performance improvement. So what used to be, if you see here, 200 milliseconds is now somewhere around 116, like almost 50% improvement, right? The biggest win for us was, I'll show you here, right? So if you see before migration, right, Azure was serving, is still better. So Azure was serving around 0.78% of total LinkedIn traffic. Because none in entire world, Azure was not being treated as a best performing CDN for LinkedIn members, where from or LinkedIn users to serve the content. So it was 0.94. We don't have a data of that date. So I mean, 3.28 it still says, right? Which is if you see Akamai is taking like 60, 57, 58%, Edgecast is taking 38%, right? After this migration, the win is basically, if you see now, it's serving somewhere close to, sorry, here, 15% profit. So from 0.94 to 15%, which is almost 1500% improvement in your traffic share, right? So what used to be 0.2% now has moved to 15%. There are many reasons for it. One, it's a better service design. They have it earlier. Now they are moving to something called as Roxy, which is a Linux-based platform behind the scene. And those all contributed to it, right? And many other factors, like some internal factors, which we can discuss over here. But that was a win for us, right? I mean, latency is definitely a win, but serving just 0.92, which is negligible, right? Moving to a 15% in global world, which is, so you see, right, somewhere around 500K decision has been made for only Azure. So decision is not equivalent to your QPS. So decision is basically says that, okay, if let's say someone is accessing LinkedIn CDN, should I return Akamai or Azure or Edgecast? So that's a decision. One decision is being made, it will be cached for certain times, like 5 minutes or 10 minutes, right? So that was a win for us. Cache hit ratio, again, it was 88 to 90%. Now it's increased to 99.6%, which is better than most of CDN that I have seen, right? So which is one of the biggest win which we had. Okay, so as a part of this, LinkedIn has a culture of doing contributing back to the community. So when we decided, we never had any example of implementing end-to-end CDN for production usage. You have to read lots of documents, like what rules, how to implement it, and things like that, right? So we contributed back to the one of the project called Azure Kickstart, which is a GitHub open source project from Azure. So it's over here. Somewhere around 12,000 stars they have, right? So around 12,000 stars. So we basically decided to contribute back to it so that if someone in future, right, try to implement AFDX, they know how to do it. They can simply do it by just clicking one button. And this model has been published on docs.microsoft.com. So if you go over here, basically it loads, and then you simply click deploy this thing, and it deploys a production grade CDN for you. So you can say deploy to Azure, right? This has been contributed by us. As a other part of thing which we have, so when we did IAC, we migrated it. We write IAC is nothing but whether Terraform or any, they are code, right? And it has to be tested in some way, right? So whether you write a DSL language, a GPL language, it has to be tested in some way. So Microsoft has, you say a general or not general purpose, a best practice guide, which is known as ARM TTK. So Azure Resource Manager, some template test kit, something they have, right? I don't know the full name. So we started using it, and then we found a very old bug, which is bug number 635, right? Which we were using it, and so there are two ways, right? Either you wait for Azure to fix it, or you fix it because it's open source, right? So we decided, it was open on 12th of April, when soon after when it went GA, and then we fixed it somewhere around on 18th August before our migration, right? So we contributed back to it. And last, so it is GA now, which is on version 0.14. Yeah, I have not added it, but I'll show you, right? So why ARM TTK is important, and why all this test, how do we test our CDN infrastructure? So, which is kind of, if I go back, which is this strategy, right? Testing a CDN infrastructure. So, LinkedIn has, I showed you 4 properties, which are major properties, but in general, if I show you, right, so we have close to 27 properties. 4 is a mean, but these are the properties that we have. If not visible, I'll just zoom it. So like we have, forget about example one, we have Ambry, badge, media, and all, like China, DMS, and all things, right? Now, so these are the properties. Now, if I show you within the properties, there are things which says groups. I'm just talking about Azure, right? So if I show you within this property, how many groups we have, and you keep scrolling down, it's not feasible to test all these things manually, right? So we have our own tool called CDN CI, which is which we have written as a part of Edge Engineering, which we run daily, not daily, hourly. It generates all our CDNs, not just Azure, but Akamai, China, everyone. and then it sends a report, okay, this test is failing, this is failing, and likewise. For example, if I run just a test on LinkedIn badge, right, it's the smallest property, so it takes some less time. So it runs test, it let us, we'll get to know like what is the current state. So it's all the tests are passing. So object exit, it can be cached, and likewise, we have so many tests, right? So these are our testing strategy. I mean, there is no framework as such available in market which says that you can test, and that is where we have to build this one. Ramping strategy, again, we use Redaxis for it. So in Redaxis, you can say route this percent traffic to this particular CDN or to this one. You can also say that for India, route 20%, but for, let's say, Singapore, route 80%. So that granular you can work Redaxis, and that is really helping us. Last but not least, single CDN test, which is kind of stress test. So what we did once we had a internal confidence that, okay, it can work, it can handle the scale, we ramped down Akamai and Edgecast, everyone. So it was for almost 3 to 4 hours. Azure was handling the entire traffic for LinkedIn all alone. No traffic going to Akamai. We were all monitoring our systems in graphs and everything which we have, right? And it worked perfectly. And that's where we concluded that the migration is being done. So in general, if I have to summarize, so whenever you, so the learning is like, the learnings basically, when you migrate it, you gather as much metrics as possible. Gathering is one part of it, but analyzing those metrics is very important, right? Second, you should have certain test cases already.
Okay, time check, 5 minutes.
So you should have your test cases, which you should verify. And then we believe in not doing a lift and shift, but when you do any migration, you should also check your tech debts, which you have introduced as a part of running your old infrastructure and trying to fix that. So, thank you.
Thanks, Yogesh. Hey, thanks for the great presentation, but somehow the time is over and we'll be having 5 minutes for question answers. But anyhow, our speaker will be on the floor only, so you can reach out to him and ask the questions.
So Yogesh, one question I think for general interest. Generally, you are talking about a lot of GUIP while serving the traffic. So what are the different works that's available in open source now to an updated GUIP database? Have you checked it? Or, for example, the user from India or user from Singapore, how at the back end you are referring to a database of IP sources and stuff?
There's no database. It all happens on runtime, right? So as I mentioned, it's a RUM data, which is real user monitoring data, right? So your browser decides which is best CDN for you, right? So when, for example, if you're trying to access from Singapore, right, we basically have certain JavaScript, we call them beacons, which is being added to the LinkedIn CDN, LinkedIn.com, right? So once you hit LinkedIn.com, it loads, and that's where it makes a decision that for this location, for this browser, for this ISP, this is the best performing CDN, and then it returns the response to you. So there's no database which is being maintained as such, right? It all happens on runtime. Yeah, and because of the DNS, once you get a first response, it will be cached for a certain time until your TTL expires, right? So when you implement the database, you calculate, things get slowed down, right? So as much as stateless is possible, we try to do that.
Thank you.
Yeah, I mean, any static content, right? So, I mean, when you upload your resume on LinkedIn.com, right, it's a PDF format, so it gets served, right? So, yeah, so question is basically, can Azure CDN serve PDF, right? So any static content being PDF, image, or I mean, you can even serve dynamic APIs, right? I mean, this, yeah.
So excellent talk, Yogesh. My question is around how can you touch base on how do you handle DOS, rate limiting, and how do you handle the dynamic capacity? You know, as you see a change in your content media, how your capacity, how your CDN providers dynamically react to that. So do you see that improvement as part of your migration strategy? So I'd like to hear more from you on that.
So before we migrate, right, we do a vendor assessment, right? What is the maximum bandwidth they have, right? For example, one of the CDN providers we have, they can serve a bandwidth of 200 terabytes per second, right? our bandwidth is maximum 100 GB per second. So at any point of time, they have enough capacity of serving those things, right? So we don't, I mean, in CDN specifically, you don't want to do auto scaling and all, right? Because that slows down the entire thing when you trigger auto scaling. For example, I'm talking about in terms of AWS, right? So you auto scaling triggers, it adds to your pool, then it comes healthy and then it serves. We don't want to go into that. So we do a vendor assessment, like, for example, we have a capacity of this thing. Can this serve this capacity, right? One is that. Second thing, the number of POP locations, right? So if let's say there's hundreds of CDN providers, for example, right? We want to have as much as POP location, which means as local as possible. For example, in case of Akamai, they have majority of POP location across the world. So for example, if you go to Akamai global.akamai.net, you will see how many POP locations they have. It's live being introduced over there, right? So the capacity planning is mainly on the vendor assessment side. We gather the data as in like what is the max bandwidth they have, the number of network they can serve. Sorry, the number of network they have, isolated network. If one goes down, do have the redundancy for serving that content to us, right? So those are the things that we take care of. These are all the CDNs, right? Until you are not having your own CDN, you cannot basically you cannot influence them to increase the capacity, because Akamai, right? You are not just the one client for them. They serve the global things. So what we do from our side, we first do the vendor assessment, which is more important. And vendor assessment includes multiple checks, like, for example, capacity, availability, number of POP locations, number of networks, right? POP is one, network is one, right? For example, if there is an event happening, for example, FIFA is happening, right? What is the noisy neighbor issues, right? For example, if someone is using FIFA, it should not impact us, right, at any point of time. So the noisy neighbor thing, all those things has to be checked. And based on that, we onboard to any CDN, right? So we started long back. We used to have Fastly also, right? Then we moved out of Fastly to Akamai. Then we added Edgecast, which is the new name is Edge.io, and then multiple other CDNs, as I mentioned. Yes. So for DDoS, so by default, all CDN providers have something called as WAF, right? So they do implement WAF, but for cache busting thing, right? So we have to protect our origins, right? If someone, for example, if I try to access a CDN URL, which is, let's say, www.example.com/abcd, right? And at the end, I say query string Q1. So if it is a miss on the CDN, it goes to the origin, right? So that is known as cache busting attack. In order to protect that, we use WAF. So we use WAF from Azure, and on the CDN side, by default, CDN, I mean, that's what I told. In the vendor assessment, we check for what WAF protection they have, what is the automation. For example, Akamai has something called Akamai Ghost, right? Which basically, if something goes bad, they basically do that. In terms of Alibaba, they have something known as noisy neighbor thing. For example, if, let's say, example1.com, the other company is making a noise, they put them to a black hole, right? I mean, they say that you go to black hole, but I'll let other customers serve the traffic, right? So that's it's a different strategy with different VDN, and you have to basically see what best fits for you.
So early on, you had a slide where you showed between your DNS CNAME record, it doesn't directly point to the CDN origin. You had some sort of a traffic redirector or traffic manager. So what does that do? You're maintaining your own set of latency tables or something? Does it allow priority routing, weighted routing? Like, can you elaborate a little bit on that part between DNS and the CDN profile?
Yeah, definitely. So if I show you, right, let's say this one, right, static.linkedin.com, lscdn.com, right? So it doesn't go to it goes to Sidexis, as I mentioned, right? But after Sidexis, you see Edgecast is being served, right? So how it is being made, again, if you see linkedin.com and if you see something called as radar here, right? So you see, these are the beacons that we are firing from linkedin.com, which basically help us know that which is the best performing CDN, right? Based on that, routing happens. So if I show you, let's say this one, right? In the response, I mean, if I go to provider, this, right? So somewhere down the line, you will see Akamai, Edgecast, they fire beacon from your browser. They're firing beacons to all these things. And then we decide, okay, this is the best for you. And let this content be served. For example, if you can see for me, Edgecast is being returned. But if you try to do an lookup, Akamai or some other may come, right? So it's not round robin. It's basically based on time, your RAM data. Round robin means like one after another, right? There's the rum data, which is best for you, we'll serve from that.
Hello. Good afternoon, everyone. Thanks for joining. Myself, Vivek Lanjekar. I'm part of SRE team in Grab. I had been with Grab for last 5 years. And today I am going to present you about our metric collection journey with Grab. So my first question is, are metrics really important? I would say like, yeah, they are important. For example, hardware, software is never perfect. You need to monitor them consistently. They tend to fail, and you need to have some proactive monitoring to monitor your hardware or software. In this era of microservices, the architecture itself is becoming more and more complex. You need to have a perfect monitoring to get metrics from all these microservices to debug issues. For example, if you have any downtimes and all, in order to fix those issues at fast pace, you need to know where exactly is the issue. And for that, you need a robust monitoring. You need metrics from all those services. And of course, you can't improve like what you can't measure. You need to measure everything to improve. And always proactive is better than reactive. Some simple instances like disk going full can always be avoided if you have proper alerts in place. So we find those issues before we get to any outages. So I'll just go through what all metrics do we collect. The basic metrics like infrastructure, CPU, memory, disk, IO, server status. Then we also collect application metrics like latency, response code, exceptions. And then comes the custom metrics. These are business metrics, which are related to business, very specific to business, like number of recharges or number of rides, etc. Then there are database metrics like database performance, lag, query latency, slow query logs, or that's type of stuff. Then CloudWatch metrics, very specific metrics which are only available at CloudWatch, like CPU credits, ELB metrics, RDS, CloudWatch services like maybe Elastic Cache or Redis. And since like recently we are migrating all our services to EKS, so those EKS specific metrics are also there. So they need to be also monitored properly. And there the list goes on. For example, if I am developing a script to do some automation, I make sure that some metrics are pushed to so they can be monitored. So I'll just go through our metric journey, how we started. So as I told before, I joined 5 years back. So at that point of time, the GFG Grab was like at the initial stages. So I was lucky that I had been part of that journey wherein I had to set up the monitoring setup from the scratch. Before that, we were using a Datadog, but for some reason, like we decided to have our own internal monitoring tool to avoid dependency. And we did POC on various tools like at that point of time, the Prometheus was available, InfluxDB was there. Also, I guess Graphite was there at that point of time. We chose InfluxDB just because it was very simple. Like since the dashboards were been moving from Datadog to InfluxDB, the queries in Influx data were very simple, simple drag and drop, drop down were available. So we didn't want that learning curve for the developers, so that migration phase should to be easy. So Influx data gave us that confidence. Even setting up alerts in Grafana were very much similar to Datadog. So that's why we went with InfluxDB. And also InfluxDB has a enterprise support. So in case if you plan to scale up and have more high availability, then we always add an option to go to the enterprise support. So this was our architecture looks like. There was a Telegraph agent which used to collect all the metrics like system metrics, Docker, CloudWatch, SATSD, the custom metrics which I was talking about, even the database metric, and then send it to our Kafka. Then we had the Telegraph consumers which used to consume from the Kafka and then send it to InfluxDB. We had two InfluxDB because InfluxDB lacks the cluster support. So in case if one goes down, we point our Grafana to the backup one. They make sure we have the same data at both the places. And then the alert is triggered at PagerDuty. So this was our architecture. We decided to have Kafka in between just to avoid the data loss in case any consumer or InfluxDB goes down, we don't lose on data. And we can start ingesting the data from where we lost the InfluxDB. These were the InfluxDB statistics. Like we were managing around 4 million series, around 13 billion data points, 30-day retention period. We can't go beyond that due to the challenges with InfluxDB. Around 0.2 million requests per day. The queries, 2,700 queries per minute. These were some statistics from InfluxDB. Yeah, we did face the challenges with InfluxDB. The first foremost issue was the cardinality issue. So this is a very famous issue with all the time series database. And it actually dies if we have some cardinality in data. And since we had opened the SATSD port to developers due to some bug, they might push some high cardinality data to the InfluxDB, some data like maybe user ID they add to the tag or something of that sort, which increases the cardinality of the series. And at some point it goes down. Even 30 days retention, it gave us, I mean, we only configured 30 days just to avoid cardinality issue. But that again had their own challenges, like audit team used to ask us like, where is the old data? And as we only have 30 days of data, that was one challenge. No horizontal scaling, only vertical scaling. Even so, we had to provision our servers to match that peak. And that was not very cost effective. Single point of failure, as I said, like if one influx dies, then we have to manually switch over to the backup influx. That was like a manual interface and downtime for monitoring. OM outages due to someone querying bad queries. Like we did fix these issues by some config changes, like adding some timeout, number of series which you can query within a single query. So those changes like somehow we managed to avoid those outages. And the last was the influx QL. Like I earlier mentioned, it was simpler, but it was not really powerful. For example, with InfluxDB, it was we won't be able to compare two metrics at like, for example, if I want to compare success with the failure or say total request with the failure, those kind of queries, those complex queries were not possible in InfluxQL. Only some basic queries were possible. So developers were always asking for this support. So we can have a much advanced monitoring system. So of course, we couldn't live with these challenges. We had to look for a better solution. The other solution was Prometheus. Since we are moving to EKS, EKS has very tight integration with Prometheus. It has very good community which supports Kubernetes monitoring. And we were only left with Prometheus as the open source solution. It's of course written in Go, so it's efficient. It works on pull method. And most important, it has a powerful query languages. The earlier challenges of running powerful queries were possible with Prometheus. But with Prometheus, same challenges, cardinality issue, again, like the famous issue with all the time series data, limited retention. We can't go beyond 15 or max 30 days. Again, we'll run out of memory at some point of time. No horizontal scaling. Vertical scaling, of course, is costly. Single point of failure, no cluster support, same challenges. So we needed to a solution, and then we explored Thanos. In Greek, it means immortal, like it can't die. Let's see. Then some features of Thanos, I can say, is fully open source. It started in 2017, so it's much matured now. Part of CNCF sandbox, around 11K stars in GitHub, 480 plus contributors, written in Go, and has a transparent governance, unlike Elasticsearch. These production users gave us more confidence. Like these companies were already using Thanos at that point of time, so we decided to deploy it in our production. How Thanos helped us, yeah. So gave a real global view. So one challenge I told, right, with InfluxDB, it was difficult to scale horizontally. What we did at that point of time for that challenge, we sharded our InfluxDB. We had a separate InfluxDB for our staging, and we had a separate InfluxDB for our production. In Grafana, we have added both data source, but you need to select, okay, which data source you need to connect. So, but with Thanos, that was not the case. It gave us a real global view, wherein the data source is same, and you can access all the Prometheus or say all the clusters at same data source. It gave me a unlimited retention. This was a dream for me, at least for any open source project. I can query around last 2 years of data, and it was possible via Thanos. It gave high availability, and horizontal scaling was possible with Thanos. And it did give additional bonus points like seamless integration with existing Prometheus. If you have existing Prometheus running in your environment, no issues, you can go ahead. You don't have to start your deployment from scratch. You can use your existing Prometheus. It's just an add-on which you want to add with your existing Prometheus. It's very easy. Minimal number of dependencies. At this point, like we did explore Cortex also. Cortex is similar, not similar exactly, but they are both part of CNCF. But I found it a bit complicated. It had many moving parts in it. Just to avoid those complex architecture, we went with Thanos. Of course, it saved us cost since we don't have to go vertical. We can go horizontal, and that too on demand. So I'll just go through these brief components which Thanos has. One is sidecar, query, store, compactor, receiver. I'll go in brief one by one, I'll explain in detail. The sidecar, right? So this is how, if you see at top, this is how a typical Prometheus setup looks like. Prometheus will scrape the target and store the data to SSD. This is the typical Prometheus. But with the introduction of sidecar, you see, in the front, it's same. Nothing changes at the front. Prometheus will scrape the same targets, save the data in the block store, blockwise in the SSD. What we do add here is the sidecar. What sidecar will do is sidecar will read this data and write the data to object storage. This object storage can be anything, can be S3 in case of AWS, can be Google Cloud, Google storage in case of Google, maybe Azure Blob in Azure Data Center. In Data Center, you can use MinIO also to replace this. So what sidecar will do is it will get the data from Prometheus disk and send it to object store. So this is also like if you see the parameters which you pass with sidecar, I'll not go in detail. If you see, we open a gRPC port. On any port, we can configure it, a Prometheus URL. the TSDB path, the path where the Prometheus is storing the database, and the bucket.yaml file, which will have config for accessing that bucket. And min time is like what is the minimum time you want to keep the data on disk that can be configured. Here you can see we are opening a gRPC port. I'll go in detail in next slides, like why gRPC protocol is being used and not a simple HTTP like what Prometheus does. The next component is the store component. As we saw in previous slide, like we are sending the data to object store, right? So that store, that whatever the data which is lying in the S3 or Google storage needs to be accessed. And there is another component known as store, which can query the data from the object storage. This is accessed via querier. I'll come to that querier part in later slides. But the main goal or the main objective for the store is to access the data which we store in S3. These are store parameters. Nothing much here. We open a gRPC port, config, same config file to access the bucket.yaml, max and min, like how much data you this is responsible for. The next query is compactor. Compactor, so as we saw, right, sidecar will just push the raw data to the S3 bucket. Raw data means like that is very rich data. It has high resolution. For example, if you are querying from Prometheus for every 15 seconds or every 30 seconds or 1 minute, that is very rich data. And you, if you are querying like 1 year data, no need to pull that much data. So what compactor will do is, it will, in this diagram, it will copy the blocks on the disk. It will compact as in not gzip or something. It will aggregate the data and it will reduce the resolution of the data to maybe 5 minutes or 1 hour or maybe a 1 day also, and then send the blocks back to object storage. So this is the role of the compactor. So whenever we query object storage, and if you are querying data for like more than a year, then it will access those blocks which have very high, very less resolution, maybe 1 day or maybe 1 hour, depending on the query we fire. So coming to the most important, one of the important component of Thanos is the querier. If you see here, in this case, we are accessing sidecar via store API or gRPC protocol. So here querier is just playing a role of a simple proxy. Whatever query we are running on querier, these queries are PromQL queries. It's proxying to the Prometheus. Earlier, what used to happen, we used to directly query Prometheus, but in this case, our queries go via querier. Here, it's not playing that important role because it's just proxying the query to the Prometheus. But in next slide, what we can see is we have a multiple Prometheus. For example, in our case, we have Prometheus for stage and we have Prometheus for prod. This Prometheus is scraping independent target. That Prometheus is scraping its prod target. Now what querier will do is, I mentioned, right, it opens a gRPC protocol. What is the role of the protocol is the sidecar will always keep updated the querier that what data it has. So querier know if someone is querying for prod data, which SOAR API it needs to connect. So in this case, if someone queries for stage data, querier would know by that gRPC protocol, okay, this data is with this stage Prometheus, the query will only land to Prometheus stage. And if you want data from prod, via querier, it will go to prod. And even if you want data from both stage as well as prod, it will merge the data and show me the data in Grafana or whatever we choose to draw the graphs. So here it's playing an important role to merge the data, which was earlier not possible with our sharding also. Now, how does it help in high availability? Same architecture, we introduce one more replica in our production. Of course, we need to have a redundancy in our production. We have 2 replicas in our production, one replica in stage. Here what happens, it will do a merge as well as deduplicate. Someone queries for prod data, querier knows, okay, these 2 Prometheus has prod data, it will query both. It will receive data from both if both are online. If not, then only from one. And then it will, if it receives the data from both, then it will remove the duplicate data. If it receives from one, then it will it will not deduplicate. If it receives like half data from this Prometheus and half data from another replica, it will stitch the data and reply the query. This is a simple architecture, a high-level architecture of querier. From QL query comes to the querier. It pre-filters the data, fans out the queries to all the store API depending on its intelligence, merges if required, deduplicates if required, and returns the query. So some basic parameters which we pass with queriers are, of course, we open a gRPC port. We open a HTTP port, which is accessible from, say, Grafana. We can add endpoint, Prometheus endpoint on this port in Grafana. The query replica label, on which label it knows like which all is replica and all. And the stores. In previous case, we only had 3 stores, stage 1, prod 0, prod 02. Okay, so coming to the next component is the Thanos receiver. So in our previous examples, what we saw was querier was pulling data from the Thanos sidecar, depending on the query we put. But in some scenario, we might block the ingress, right? Here, for suppose if these clusters don't have ingress rule, I mean, we don't want to allow, in some scenarios, we don't want to allow ingress traffic. But what we need to do is to push the traffic. So in that case, receivers comes in picture. So this is a typical, but to explore this feature, the Thanos is exploring the remote write API. So Prometheus either can write to disk, or there is an option wherein you can say Prometheus, okay, you write to the external Prometheus, which may be a central Prometheus. So what we do is we deploy Prometheus and say Prometheus, okay, write to the external remote write API, which is nothing but our receiver. So this is how a typical push metric would look like. This is just the Prometheus. Just I need to make clear, there is no Thanos component here. We only have configured Prometheus to push metric to an external endpoint. And that endpoint is of our receiver. So all the clusters will start pushing the metric, whatever they receive, so to the receiver. It won't store the data in the disk. It will just start sending the data to the receiver. And that is the role of receiver. It will receive the data, which will be queryable by the query component. But yeah, you can see there would be a scalability issue. For 3 clusters is okay, right? But what if we like keep on growing and we reach the nth cluster, and then since it's a single point, right, it can explode just because like we are sending too much of data. In that case, how do we manage this situation? So what receive supports is a hash ring. We can scale receive component with the hash ring method, and we can scale manually. It supports auto scaling also. So depending on the traffic or our configuration, we can scale it horizontally, most important. We can also have multi-tenant, wherein a single receiver can be used by multiple tenants, depending on like what exactly the Amazon is doing. They have opened a recently Prometheus as a service, wherein which endpoint we can use to send data. It's similar thing. They are using Cortex in backend, but we are using Thanos, but same architecture. So we just have the endpoint to which we send the traffic to. And this is how a typical or a normal Thanos receiver looks like. There are multiple clusters which are sending to traffic to our receivers, which is auto scalable. And after some point of time, it will write data to object storage. This object storage data is accessible as store. So, and querier has connectivity to both store as well as the receiver. So whenever Grafana query ends on query, depending on what data we are asking for, it will either connect via store or via Thanos receiver. This is a normal hash string config looks like, wherein we add the endpoints of the receiver. But here, if you see properly, there is one challenge, right? This is static. How do we auto scale this? You need to then change the endpoint and then add one more machine in the receiver, then add this, reload the entire receiver infra so that it's replicated. So how do we manage this automation? So there is a Thanos receiver controller on this website, sorry, GitHub. I'll give you a small, I recorded a demo. So I'll just show you how exactly it works. So the repo is already been downloaded, the files. I hope it's playing. Yeah, so I'll first create the namespace as like, let's create a separate namespace name as Thanos. Then I'll apply all the files which are there in that folder. This is just a basic installation, nothing much we are doing here, just for demo purpose. So what we see, these are the files which we deployed. So now we see the config, or first let's see the so I'll just say the pod. So right now there is only one pod running here. Also we'll see the config map for that particular pod. So if you see, I'm just getting, so only one endpoint is there in our config. So now what I'll do is, this is the one, and what I'll generate a traffic, Prometheus traffic. This is an open source tool. I'll generate a topic on that receiver endpoint. So any errors, it will be shown here. Right now, there are no errors since the cluster is stable. Now what we'll do is we'll add some more replicas. So for example, I'm adding 3 replicas right now. Now I'll see the pods. It has auto scale to 3. There is no service disruption. It has it's not auto scale. It has scaled to 3. This can be auto scaled with some parameters like CPU or memory. It can auto scale, but right now we are just, even if you see the config map, it has changed to 3 endpoints. So all the 3 endpoints are receiving the traffic as per the hash ring. So this is helping. We can. Just wanted to demonstrate how easy it is to scale these kind of clusters on demand.
I'm check.
Sorry. Okay. Sorry for this bit complex diagram. This is how our typical architecture looks like. If you see, we have set of EC2 boxes. We have mix of all. Right now, we are moving from EC2 to Kubernetes, but if you see, there are some EC2 boxes already. There is Kubernetes cluster here. How are we monitoring our EC2 stack? Is we have an agent running on known as Telegraph, which I discussed like in previous slide. We are using the same Telegraph agent. We are not using Prometheus exporter. We have opened a port on Telegraph, Prometheus port. So, and we have a console agent running on each of the instances. So what Prometheus will do, it will, since it has the console agent, it will take inventory from our console server, and whatever the inventory it gets, it will start scraping the metrics. So this is how our EC2 stack has been monitored. Now coming to the Kubernetes metrics, what we do with Kubernetes is we deploy Prometheus. When we create our Kubernetes cluster, Prometheus comes up. We configured it to write it to remote gateway, remote Prometheus, which is nothing but our Thanos receiver, which is auto scalable. So whenever the cluster is up, we start receiving the metrics at the Thanos receiver. And this is our query component. So if you see, query is connecting to Thanos sidecar. It is connecting to bucket via Thanos store. And whatever the Thanos receiver is writing data to S3, right? So we have configured, okay, 4 days data you keep on disk, others data you can push it to S3. So if the data is older than 4 days, it will query from bucket, S3 bucket. Recently, Thanos has introduced something known as Thanos front end. the role of the front end is nothing but it will cache all the queries in Redis cache. Whatever the query it gets returned from the Thanos, just to speed up the query response. And in Grafana, we only have one data source, which is Thanos. And with that data source, we monitor entire thing. So this is about the active series on Thanos right now. Active as in which is on the disk and not on S3. So we are touching around 18 million series on Thanos right now. These are the sample per seconds which we are processing. It's around 500K. We touch, and it depends like on the traffic, like how much, how many clusters are live, or are we doing any deployment? That depends, and we touch around 500K samples per second which are processed. Of course, it died, our Thanos. Mostly like initially, right, when we started with this project, we didn't go with auto scaling at that point of time. We had a receiver, one receiver or two, maximum two receivers we had. And one issue happened was since there were 18 clusters which were sending traffic to the receiver, and there was some connectivity issue. So the remote API by design, it is very what you say, like it will keep on retrying. If the endpoint is not found, it will keep on retrying. And the receiver by design, it won't accept stale data. So what happened was we lost the connectivity between the between receiver and the our Prometheus servers. And once the connectivity was restored, all the old data was pushed to our receivers. And that since it started rejecting all the data, it ran out of memory since it has to process so much backlog. And that time we didn't have auto scaling also on the receiver. So that was it. So then what we did was we initially like blocked all and introduced cluster one by one to the receiver, and that created stability. So we did fixes to avoid such scenarios, like we tried to limit retries in case of remote write failure. This is configurable at the Prometheus level. And also we introduced scalable receiver. So in case this thing happen, at least it auto scales and no manual intervention is needed to. Then the another was scalability, which we sorted out with the deploying it in auto scaling Kubernetes. And one other challenge was monitoring. So if I go on the previous slide, here if you see, the challenge here is Kubernetes will send metrics to receiver, and then once the receiver has the data, then only we can create alerts at Grafana. What if Prometheus dies there and we don't know anything, right? So in that case, what to do? So for that challenge, what we did was we deployed alert manager at the Kubernetes level itself. So what the role of the alert manager is, it will get the data from the, so alerts are generated at here itself. So basic alerts related to Kubernetes are generated at the cluster level, and they are directly forwarded to the PagerDuty instead of creating alerts over here. So that's how we fix that issue. So what we do right now is whenever we provision a EKS cluster via automation, we deploy Prometheus, we deploy alert manager with all the basic roles, which alerts us if something is wrong with the Prometheus, which is running on that instance itself. So yeah, these were the challenges and the remediations which we applied. Current, yeah, as I showed you before, right now we have around 25 TB data on S3, which is all queryable. We can query. So we started this project around 1 year back, around 14 years back, and we have all the data, and we can query. We can go back in time without any issues. We serve around 2 million requests per day, 2,700 queries per minute. Thank you.
Thanks, Vivek. We'll open floor for the questions.
Vivek, very informative, great talk. We got to learn a lot. One question is, people normally debate, should I go for a managed service on cloud or build everything on my own on cloud and then deal with the complexities of a large distributed system? So I'm kind of wondering, why did you take this route and what challenges you are facing? And have you built the right set of operators to build everything on the fly as a one unified service? Because I see a lot of complexities there and it's not easy to manage. So I would like to understand and hear out what kind of learning experiences and what challenges you face there.
Yeah, we, like as I said before, we used to use Datadog before, but simply it's not cost effective, it's costly. And audit requirements are also that the data should not go outside. So we need to comply with that also. So we need to have something internal. So we did try to have something internal. We did face challenges. And yes, these systems are complex, but since there were outages, of course, but we make sure that most of the things are covered within the monitoring and are they resolve on their own. Of course, there are some scenarios wherein there are outages. As I mentioned, there were few outages, but we took the call to we had an option to go with something like Datadog or Signal FX. There are multiple platforms, but we decided to have our in-house, mostly due to cost and the compliance issues.
Hey, Vivek. Indeed, an insightful talk. So I actually was more interested on the compactor aspect. I think cardinality, the scalability issue is like a universally legit issue. I think all of us who are running things at scale see it very often. So my question was, what is your retention period for a granularity of, say, minutely data? And what is the retention for your hourly or daily data? So how do you configure your compactor in such a way that you have minutely, then you flush the data after 2 weeks, and then, okay, anyway, I'll let.
Yeah. So I got your point. Right now, we are not flushing the data. We have all the set of data in our S3. For example, the data is available at 30 seconds granularity, 1 5-minute granularity, and 1 hour granularity. It depends on how we are querying the data. For example, if I want to go back a year back on like a 31st of September, a year back. So, but if I try to get data for a year, for that particular hour in that day, then if we don't have that data in S3, we won't get that granularity. So what store will do is, if you are expecting the data to be like 15 second, have a granularity of 15 second, it will access that block. That block is not flushed. That is there already. But if we try to get data for a year, so say in a single graph, normally these are only accessed via Grafana. So the queries which are fired goes via Grafana only. So Grafana is intelligent enough to know how much resolution data it needs, and depending on the request, it will access only that block. So for example, I have one block of say 15 seconds cardinality. There will be multiple blocks which will be created by compactor depending on the resolution. So depending on the query, the store will access that block which has that which matches the resolution which I'm asking for. I hope.
What's your? Oh, thanks. That sort of answers my question, but like, sort of a follow-up question is like, what is the latency when you query? Because we have seen expensive queries taking a lot of time, and then like.
Are you on Thanos?
Not Thanos. Like we have something in-house built. So anyway, I think the issues remain the same irrespective of the fact.
Okay. So latency. Okay, I'll show you. Okay, I don't have the 1 second. latency is not that much. So for example, we have caching layer, right? So
Or a yearly data, like I'm talking about, like not the rich ones, like the yearly data. If I want to query last 2 years of data.
okay, so I'll tell you this real life scenario. People, normally developers won't go that back. Normally developers are only concerned with the data, which is maybe 1 day back, 3 days back, 7 days back, maximum 14 days back. We run the developers only, maybe auditors do run the long queries if you want. But in case of running like 1 year data, there is not much latency as per my observation, maybe around 1 second or 2 seconds mostly.
That seems pretty quick. But I think like most of the ML stuff you want to train, I think that's where you'll need that historical data. But yeah, we can take it offline.
Yeah, but this our use case was just for monitoring. So we till now there was we didn't face any latency issues related to latency.
Okay, thank you.
Okay. So on a short notice, folks, we can also start the line. So questions we can take with it too.
Thank you.
Hey, so so I have a question based on the answer that you gave, that in most cases, we don't need a data older than 1 month, right?
Yes, yes.
That's the thing. So how does your object storage policy looks like? For as of now, you're putting everything onto S3, which is kind of a hot store, right? So do you have some policies around moving data to cold storage like Glacier?
No.
Something. So everything remains on hot, right?
So Thanos can't query Glacier. It can only query the data which is stored on S3. So no.
No.
So, yeah, it was really awesome slide. I just have one question. So I saw Thanos has a component, Thanos store, right?
Yes.
Is that horizontally scalable?
No. So sorry. Okay, compactor is something which can't. We need to only have one, but store can be multiple stores.
Okay. And
so querier, depending on which store is available, it will query that store. It doesn't matter there are multiple stores, because it has to only read the data and give it back.
And does store actually stores data on the disk? Or?
Yeah, it first copies the data on disk and then sends the data.
And the service is running on Kubernetes?
We only have receiver component on Kubernetes, not those are running on EC2. We might move, but right now only receiver, just because of that auto scaling part. And we faced issues in because right now our most concern is our EKS monitoring. Since we are moving out of EC2 to EKS, so we need more scalability there. So we only have a receiver component running in EKS.
Awesome. Thank you.
Thanks, Vivek. Thanks, folks.
Thanks.
With that, we are opening floor for lunch. We still have 2 more talk. Post lunch, we have one talk from AWS, another from Mithun. So please be here. Thank you. Thanks, everyone. Hope all of you have enjoyed the lunch. Time for next talk. So Avilas is our next speaker. Over to Avilas.
Good afternoon, everyone. Thank you so much for this opportunity to the hosters and the ones, of course. Thanks a lot for giving me this opportunity. Happy to be a part of this LSP event. So just to give a brief introduction about myself, my name is Abhilash. I work as a cloud support engineer with AWS. I work with AWS for a little over 4 years right now. So I primarily work with serverless technologies, contact center technologies, and managed AI ML services. That is pretty much about me. So maybe in the next 40 minutes, what we'll be looking at is how are we scaling contact centers for intelligent customer experience. So almost all of us here would have interacted with customer support or customer, help or assistance at any point in our time, right? Be it, any hyperlocal applications or e-commerce, or take any product or even enterprise products. Support is something that is very crucial after the sales happens for customers, to keep using it whenever they, get any queries or questions. Support is something that is pretty crucial. And over the period of time, organizations have evolved to provide a better customer experience. So how do they do this? By providing a better support, which in turn relies on different features, right? So today, we'll be looking at why contact centers are crucial for business success. So if we take, maybe 15, 20 years back, somewhere around the late 1990s or even the early 2000s, it was mostly PSTNs, right? So whenever there used to be some issue, we used to call, the helpline, we get our queries sorted. But over the period of time, it did evolve. And why are organizations today stressing more on this customer experience? So for example, if we take a simple food delivery app, whenever we search for help, we're given the last couple of orders. So this is personalization. So over a period of time, all these have been evolved. So then we'll see how contact center evolution came with SIP, VoIP, and WebRTC. From what started with PSTN, we are now in the SIP VoIP world. And then we'll see where Amazon Connect comes into the picture. How is it changing the landscape? So what is it doing? Followed by, we'll see the internal architecture, like how is Connect able to scale? So just to provide a brief overview, it is able to support 10,000 agents at a given point in time, which is more than 10,000, 20,000 active calls at a given second for a single, customer, by the way. So if there are multiple enterprise, organizations using it, it will be able to scale up, theoretically to an infinite level. But yes, it has a very high scalability. We'll be looking at how Connect achieves this. Followed by a quick demo and a Q&A session. Yeah, before we jump on to the topic, a brief, context about what my team does. So I'm a part of, support engineering. We're a global team. We work with customers across the globe, right from, startups to enterprise level customers. We collaborate with cross-functional teams, which are product development teams, solution architects, customer solution architects. We work with them to achieve their use case, to customize how they'll be able to, architect their workloads on AWS. And currently, when I joined AWS back in 2018, we were around a team of 300. But over a period of time, I think 4 years down the lane, we are around 1,600 plus, team. Again, there are multiple internal teams for each of these domains, like, networking, big data, and so on. Primarily, we do help customers with troubleshooting their technical issues, working with them, be it any of their environments, UAT, dev, QA, prod, so on and so forth. And apart from this, what we also, look for is try to see how we can, empower our customers more, which means like self-service. For example, if a customer or a client is raising a case with us, we try to, incorporate, intelligence, if I should say, to grab the customer's query and see if there are any resources that can assist him. And we also provide self-service automation scripts. So when I say automation scripts, it's something like, let's say I have an issue with this service, I want to pull the logs. So all these things are performed, with the help of self-service and automation scripts. So we do provide that as well. And lastly, we, of course, overall, just to provide a picture, we do help customers in their cloud journey, right from when they are onboarding So we do also collaborate with multiple teams to, have multiple sessions for customers during their launch times or critical events, so on and so forth. Fine. Now let's see why contact centers are crucial for business. So 15, 20 years, it's just calling a number, getting help. An agent picks up the call, sorted, done. But now if we see, as humans, we wouldn't like to wait, right? We want to get everything, delivered or addressed at a quicker rate. So it is always not feasible to have, a caller or a customer for any organization who wants to provide a good customer experience to have them waiting in the queue. So primarily what they try to do is try to, again, enable customers as much as possible through self-service journeys or IVRs. So a simple use case can be like, let's say I have a travel organization. So my customer books a train, they get a PNR. So basically if customer wants to check the PNR status, he can just call, he can dial the PNR and he can get the status. So no agent is required here. So organizations and as business use cases evolve, we are moving to a world, where self-service is starting to peak. Then skill-based routing. This is something which is very crucial. So for example, we usually go to support or, customer assistance when we need some help, right? So the infrastructure that organizations use to, scale their contact centers or build it needs to have a skill-based routing. For example, most of the organizations have, what we say, high valued customers or their top customer bases. So they would always want, the most, skilled or tenured engineers to be able to address those issues. That is where skill-based routing comes into picture. And if we go into the traditional contact centers where we just started, this is something that is that wasn't there, but now it has evolved. So organizations look for this. After this, it's multilingual support, right? So now everything is global after the pandemic. So you have customer bases all across the globe. You want to provide more localization, more personalization to the geographic location. So multilingual support is something that's very crucial. And apart from all this, this is the most, key factor, at least, personally for me, incorporation of AI capabilities. For example, if I call just by my number, I need to get all the details, my previous case history and everything. There are multiple CRM applications, but apart from that, when we talk about customer experience, it's pretty crucial to, emphasize on sentiments. For example, if I'm speaking to an agent, I'm pretty frustrated. Organizations are now trying to, catch the sentiments in near real time, and mitigate the customer pain. So incorporation of AI capabilities. And the first 4 points that we see here are from the customer side of things, like an end user side of things. But the fifth one is reporting. So when a company has agents, providing support, ultimately they want to measure the productivity. Monitoring as in not, monitoring or something, but, just, how do we say, metrics, like how many, issues are they taking? What is the time taken? So all these, this is not the end of the list, but these are the key requirements that, organizations look for, and they play a very crucial role in the business success. So what was with the traditional contact centers and how is it moving forward? So if we take traditional contact centers, everything is in-house. So right from on-prem management, like procuring servers, switches, then you need your media gateways, your session border controllers. And if you are incorporating AI, then you need NLU, natural language understanding components, which will, capture the caller when they speaks, then automatic speech recognition. So all these things, in the traditional contact centers were not available with a single vendor. Maybe after the time they would be, but initially, or, in the majority of the cases, there wasn't a single vendor or everything where you can get under an umbrella where everything is provided by, one entity. And the most difficult part here is the compatibility. So we'll take one simple example. When we call to a call center, the calls go via PSTN or, POTS, public switch telephone network. So when the calls PSTN, it's as simple as a similar analogy could be like how, your DNS works. So for a call to get established from the agent or, from the caller to the call center, there needs to be a dedicated line, or you can even call it as circuits. So these needs to be in place. And there are other components, for example, CTI, computer telephony integration. So in the previous slide, I was talking about providing a personalized experience where we have CRMs, CRM softwares where, you can get the number, get the entire history of the customer. So all these are provided under different vendors, and making them compatible with each other is a mammoth task. It's not as simple as it sounds. So, if you see the image here, we have multiple things. So let's start from the top. You have the server rack. You need to procure servers, then your carrier PST, and you need to procure numbers, establish dedicated lines. Some of the organizations, use SIP trunks, private branch exchanges, then ultimately, the phones, the desk phones, or if they are quite advanced, they would use soft phones. So these software and components have to be procured. Then licensing is again a challenge, and making all of them work together as unison. So it isn't as simple as it sounds. So the challenges were all these, required upfront investments and costs. So when an organization is starting to support customers, initially their customer base would be a little small. So as the product enhances, their scale grows. So right sizing becomes an issue there. You need to plan well in advance what the capacity is. And this may go better or it may go south. So maybe let's take an hypothetical scenario. If a product doesn't scale, then all the upfront costs, are not of value there. And managing all these. So if there is failure in one of the things, there are multiple components that may get affected. For example, media gateways, where, your media, when you speak, the media, is relayed. So if that is gone, then your entire contact center gets hampered. So managing all these becomes a pain. Infrastructure management, failures and outages. And on top of this, having a DR mechanism. So what if I have an on-prem, call center here? This fails. So what happens next? So customer is kind of orphaned without any helpline. And again, incorporating intelligence, sentiments, and everything. Primarily, we look for the components that are required to set up a basic contact center, and then build on top of it, like sentiment, in real time, when I speak, the software would be able to catch my sentiment. All these things are pretty crucial, and these are major challenges, in contact center environment. Scalability, of course. So if you're going to have 2,000 or 3,000 calls, this depends on the number that you procure. So if you take a DID number is something like it wouldn't be a right analogy, but you can consider it as a simple mobile number. A TFN are toll-free numbers, which begins with 8XX, 1800, 1833. It's of the form 8XX. Toll-free numbers provide redundancy, but DIDs, they have limitations on the number of calls that can go via a specific session. So all these were big challenges there. So before we move on, we'll also see how, contact center evolution came from PSTN, then SIP VoIP, and how this helps in scalability. So we saw that PSTN works via multiple, it works via telephony. But as time evolved, I think around 1996 is where, SIP came into picture, and it was put into the RFC standard in 1999. So let's take this example, and we'll see the flow of SIP here. We have two peers, peer 1 and peer 2. Peer 1 is Alice and peer 2 is Bob. So what is SIP? What is VoIP? What is WebRTC? Before we go into in-depth here. So SIP is an application layer protocol, a session initiation protocol, which is used to establish connectivity between two endpoints on an internet. This kind of forms the base for VoIP as well. And SIP in turn uses STP, session description protocol, which we'll see in some time. So let's say peer 1, Alice wants to talk to Bob, peer 2. So what will happen is Alice will send something called as STP offer, session description protocol offer. Now, what will this contain? So we initially talked that there should be codecs, right? So when you communicate over, internet or any audio file that you're using, it'll have something called as codec. So peer 1 and peer 2 should use compatible codecs. As again, a similar analogy could be like the SSL handshake. So initially the client hello goes and you decide what TLS version you support, and then the client certificates get exchanged, so on and so forth. So first thing is peer 1 sends the STP offer request that contains, the timeout values, the date and time of the call, the timestamp, basically then codecs. So this is first sent to the signaling server. So signaling server is again a third-party server which facilitates the connection establishment between the two peers for them to communicate. So the first thing is STP offer. This goes to signaling server. Signaling server then sends this to peer 2. And peer 2 will then decide if it wants to accept calls or not. If it rejects, then done. If it accepts, it will send us STP answer. STP answer will again contain the same data. It says the same codecs, timing, and once peer 2 agrees, then peer 2 will send the STP answer back to signaling server, after which ICE, interactive connectivity establishment, ICE candidates. So that will come into picture, which we'll see in a minute or two. Okay, now peer 1 and peer 2 have their connection established, but we have something called as peer-to-peer audio video exchange without the help of servers. So this is like peer 1 will directly exchange it to peer 2 without going through any server component. So how this is again managed is with the help of stun and turn servers. So stun server is session traversal utilities for NAT. So every server, peer 1, peer 2, they sit behind firewalls, or they have private IPs, right? They basically sit behind routers. Now, if peer 1 wants to communicate directly to peer 2, they need to know the endpoint. So how will peer 1 and peer 2 know their IP addresses? That is when they ask the stun server, hey, what's my IP? Stun server will return the response. And peer 2 will also do the same. So now peer 1 and peer 2 have their IPs configured as well. We have something called as the turn server here. So turn is traversal using relay around NAT. So what is the difference between stun and turn? Stun server is something that is publicly available for free, okay? But turn server, it is a stun server with added functionality wherein you can relay media as well. So it can still go here for NAT traversal if peer-to-peer connectivity fails, or if the peer-to-peer is supported, it can directly go via the peer-to-peer audio exchange. And stun and turn servers help facilitate that. So once the IPs are obtained using stun servers, peer 1 will have its port and IP. Peer 2 will again have its port and IP. This is the ICE candidate. So ICE is interactive connectivity establishment. So both peer 1 and peer 2 will now have their IP addresses through which they'll be able to exchange audio and video. So this is currently how SIP is working. So WebRTC uses STP again, session description protocol. Okay, why Amazon Connect and what difference does it bring? So this is 100% cloud-based. So all the challenges that we saw in the traditional contact centers, this kind of takes care of everything. All I need is a laptop and an internet connection to scale up my entire contact center, even with 1,000 or 2,000 agents. So a couple of things with Amazon Connect is it provides customization or personalization. So it has a very powerful integration with serverless components. Like most of you would have worked with AWS Lambda or DynamoDB or even step functions for that case. So as soon as the call comes in near real time, the number can be fetched, the caller number, you push it to Lambda, Lambda can query DynamoDB, and it can give you the response. All these could happen in, a few milliseconds, not even seconds, few milliseconds. But of course, the querying latency would depend on how big your database is. But in general, this is possible to do with, milliseconds with right sizing. Then self-service configuration. So designing IVR or contact flow is very simple. Like literally it is just a drag and drop. So there isn't a specific thing that would require to, a skill that is required to scale this up. You can just create a simple contact flow and it would be able to scale up to 1,000 calls or even more than that, so to speak. The third one is the open platform. So you can have integrations with multiple CRM components again, like Salesforce, Zendesk, ServiceNow. And again, the last thing is integration with AWS ecosystem. With the multiple add-on features apart from this, like voice ID, you can have security using voice. For example, most of the times you have call centers where agents say, can you please provide this for confirmation? Like they ask for date of birth or your email ID and so on. But here, voice ID is a feature wherein, again, incorporated with AI/ML, Once you register your voice, you can just speak for 10 seconds without the call even coming to the agent. Once the call is authorized, once your voice is authenticated, you can be, you'll be passed on to the agent. And all these logics with the help of drag and drop for the entire scalability. Yeah, so the different integrations that Connect provides is storage. This is with AWS ecosystem, but again, you can integrate this with any provider with Lambda. So have a Lambda, can make API calls to any of these providers like S3, DynamoDB, AI services like Comprehend for detecting sentiments, reporting, then app integration. So all these features are available inbuilt. So moving on. Now, this is how Connect scales. So this is how Connect is internally architected. So we all might have come across EC2 instances, right? Where you can just turn it on or turn it off. Connect is something that wouldn't provide that. You either have the instance or delete the instance. And this is the redundancy. We'll see from left to right. So these are your end user customers in your call center. They will be able to dial to Amazon Connect using PSTN number, a DID number or a TFN number. Now the number procuring, you don't have to do anything, just maybe 2 or 3 clicks, you'll be shown the numbers that are available and you procure it. So coming to the architecture here, so Connect as an instance is, uses multiple redundancy and scalability here. It is very resilient. So for example, let's say you have your instance located in a particular region, like, Northern Virginia. So internally, it is scalable. It is redundant across 3 availability zones. So that is how it is able to scale so easily. Even if one of the, components in, AZ zone 1 goes down, you will still be able to, have disinterrupted or uninterrupted, traffic across the other, with the availability of other instances. So when you make a call, it is a number. So it goes as a PSTN call. But when it comes to the agent, Connect supports both handset. For example, I can even configure the call to come directly to my mobile using software here, which are again inbuilt, or you can take the calls via CCP or the soft phone, which we'll see in some time. So how does these 2 things happen? Now, PSTN to WebRTC. So it's like, compatibilities. PSTN, it's always analog. When you go WebRTC, it's digital everywhere. So we have something called as SBC, Session Border Controllers, which are used to manage secure sessions, in real-time call establishments. That is again managed internally in Connect. So this entire infrastructure, right from this point up until that internet, everything is taken care of by Connect in terms of scaling. So the only thing that is required when you're going to use this is you will need to just right size or, anticipate the traffic that you'll be receiving in terms of, the number of calls. So PSTN and DID and TFN. Why do we see 2 carriers here and 1 carrier there? So DID numbers are threaded to a single carrier. So this is, from the telecom side of things, that it's always threaded to a single carrier. It can't have multiple carriers here. But TFNs are toll-free numbers where the traffic can go through multiple carriers to reach Connect. So that is why we have 2 carriers here. So once the call comes through the carriers, the calls come to the Connect endpoint in the AWS cloud region, which is where we have the SPC. So if you see the 2 lines here, this is where redundancy comes into picture again. Even if this particular carrier goes down, this entire line would be cut off. So we have multiple other, lines that offer redundancy from the carriers to the AWS data center. Again, the instances you see there, please don't take that as an EC2 instance. That's basically the infrastructure that is supporting Connect. And you have direct connect here to establish extremely low latency, high bandwidth data transfer from your carriers to Amazon Connect. So this is on the caller side of things. They call to one of these numbers, call traverses through multiple carriers, and ultimately reach the cloud, which is AWS. Now, coming to this side, why do we have a ELB here and what do agents do? So when call comes here, the calls needs to be routed to the agents. So they have the soft phone or the desk phone configured, and Connect supports calls, chats, as well as tasks, where it's like an internal ticket. So agents can use their soft phone, and Connect has multiple other internal components. So basically it uses CloudFront, EC2 instance, and even internal API gateways to make use of this. So when the calls come in, there will be a signaling endpoint, which we saw earlier in the previous slide. Signaling endpoint is used to establish connectivity in real time between two endpoints. So that is this endpoint and here, Amazon Connect. So call gets anchored with Connect because the end user is using PSTN. This is using WebRTC. So the call comes in and there are two, lines that are used. So all the voice traffic runs over UDP here, which is like most of the real-time applications. It uses port 3478. These instances are load balanced so that when the calls are coming in or when there's influx of traffic, the load is balanced appropriately between agents for the calls to get routed. So moving on to layers. So Connect, again, if we see a layered architecture here, it has 4 layers. Telephony, which is again completely managed. As an end user, all I need to do is just procure my numbers that I want, either PSTN or DID. I can even have numbers if I want it for a specific area code. Let's say I want a DID number with the area code 206. Most of the customers have this use case because they want their client base to know that they have a geographical presence there. So you can use the telephony layer is used to establish a call connectivity. The contact is the one that customer calls, comes via PSTN to Amazon Connect, and telephony takes care of it. Then you have APIs. So all the deployment, the changes in your IVR, the logical phase, everything can be done via deployments and API. Metrics and reporting. So we'll see how Connect shows metrics in real time. The agents who are online, the agents who are offline. Even if there are 10,000 agents, you'll be able to query it very easily. Lastly, the contact flow, where the IVR logic stays. So we talked about intelligence in contact centers, right? So let's take an example of a simple call flow pattern. Caller calls Amazon Connect. They can choose, press 1 for sales, 2 for billing, and 3 for support. They'll be routed calls to the agents. Now, when they're speaking in real time, let's see how, call flow analytics work. Yeah, the flow would take 15-20 minutes, but I think I already have a demo here. So let me just take that. One moment. Okay. So when I say intelligent reporting, this is what Connect provides for every call. So you have something called as the contact ID here. So this contact ID is something that is unique for every call globally. So every inbound or outbound call or call transfer will have something called as contact ID. And then you get what type of call it is. If it's a voice or a chat, and then the initiation method. If you initiated the call via APIs, or was it an outbound call where agent placed a call to the customer, or was it an inbound call? Then media streams, this is audio. Then the start and end time. So you get the duration of the call as well as the disconnect reason. So this is where if the customer hung up the call, because he was frustrated or something, or if the agent hung up the call. Then the customer's phone number. So this is where I said you can personalize. You can capture the customer's number in your IVR logic and have all the data populated. Then ultimately the agent's name. So this is just a sample profile. And then the queue, what I mentioned as a skill-based routing. You can have multiple queues. So calls would get routed to hundreds of queues. One agent can even have 15, 20 queues if they are more tenured or more experienced, whatever the business use case is. So you even get the queue and the last updated. Now, if you check here, this is the customer sentiment. And all this can be run after the call or in near real time. So post-call analytics or near real-time analytics are scaling for 10,000 calls. So if we see here, the sentiment is neutral for 50% of the time. So there are 4 sentiments that Connect provides, like positive, negative, neutral, and mixed. So it's neutral 50% of the times. The conversation was only 8% positive, but it was 41% negative. And in addition to this, what I mentioned about NLU, ASR, the call center is designed in such a way that it will be able to detect silence. So if you see here, you have something called as the non-talk time for 15% of the time. Then customer talk time is 31%. Agent spoke for 53%. Within that 1 minute and 40-second duration, these are the different metrics that you get. So you can even categorize, you can set rules like this is a sample which I've set it as a complaint, but you can even set it as sales, support, business prospect, or marketing lead, or anything based on your use case. The contact center will be able to capture it. So you can still play the recording and see where the sentiments are. So red is issue detected. So all these are not only available in the UI format, you can still stream this to an S3 bucket. So you can have a Lambda function that consumes data from S3 and perform your own processing as well. Now, if we go to the transcript, the call is entirely transcript. So whatever I'm speaking gets transcript. So again, there are a couple of points. So accent is something that is still growing. So this is just before I go into that, Connect for call analysis and transcript uses Comprehend. Not sure if you heard of Comprehend, but that is again a managed artificial intelligence service of AWS. So Comprehend is a NLU text processing service where you provide a sentence, you'll be able to detect sentiments. So when I say managed, all these are managed internally by the service on a very large scale. So it should be, this is Abhilash, but again, there are certain accents that you need to configure. So it says this is made of premium support. And if you see the emoji here, it is neutral. So customer again says hello, this is neutral. So my name is Abhilash. So I was using US English. So my accent is not US English, right? So some of the words it wouldn't be able to capture. So it's also important to ensure that we use the right, dialect and the accent when we are configuring this. Now, customer said, actually I'm a customer using a product from last 3 months. I experienced something very bad. So if you see the emoji here, the sentiment is bad. So Connect provides a very granular, level at which you'll be able to capture these sentiments for every call. And it just doesn't end here. So everywhere, if you see, so sure, I'm so sorry to hear that. I got your query. So here again, the sentiment is something that is not green. It's red, which is negative. So that is why it's red. So again, customer says like, no, it's not about it. Sorry, I just want my money back. So all these are negative sentiments that a Connect will be able to do this in real time. So once you're able to capture the sentiments in real time, it is easier to mitigate all these in terms of providing a good, customer support. Apart from that, you have all the other metadata, the time of call, the queuing mechanism, so on and so forth. Now, let's just take a look at the contact flow. Okay, sorry for the mess, but this is a pretty, large contact flow that we have here. So I was talking about IVR logic, right? So you don't have to write any specific script for this. All you have to do is just use, drag and drop to scale. And the same logic can be used for chats and calls as well. So before we go into this, I'll just try to show a quick demo. Okay, let's say I want to chat.
Yeah. Time check. 5 minutes.
Okay, I'll just show a small demo for chat. Let me just refresh this once. So there are certain constraints like your audio shouldn't be shared. So Zoom is still using this. So let me just refresh it once. Okay. So this is an example of, live chat, and we'll be seeing an agent getting a chat here. So the example that I have here is a self-service journey again. So I have integrated Lexbot with Connect. So the contact flow that we have here has this Lexport integration, everything with the help of, a drag and drop. So let's say I want to book a car. I'll just provide one. So it's asking me in what city. My bot is configured in such a way that it will accept only bots from US cities. So let me give Delhi and see what it says. So all these are logics that you can incorporate within your Lexport, your Amazon Connect. So Amazon Connect will act as a channel between the end user and the Lexport, and everything will scale. So let's say Seattle. Let me give tomorrow. When I want to start my rental, basically, I want to rent it from tomorrow. So what date you want to return the car? Literally, if I give yesterday, it shouldn't accept, because logically it is not possible, right? Let me give that as Monday. So it will take the immediate Monday, the day after tomorrow. Again, this is for the age check. Our driver should be more than 18 years. Let's go for luxury. So if you see the date, it says from 25th to 26th. And when I say book, yes. Now I'm getting a chat here. So where, end user can directly interact with the agent. So I've made this as 2 windows because this is the actual customer chat. So you can see the entire conversation with the bot, what I mentioned, and I can also start chatting. It should appear here. So my agent's name is Amazon. So I just gave yes. So this way, you will be able to, interact with, you'll be able to set up a contact flow, which helps in, not only self-service, but direct agent integration, and everything with the help of logics like this. Yeah, this would look, a bit more complex, but it's something that is very simple. You can log how the call goes. Sometimes agent says, I pressed 1, but the call did not go through. So you have the login mechanism. You have the play prompt that plays the, welcome message, welcome to IVR self-service agent, so on and so forth. So this way you will be able to configure your contact centers. And this configuration is the only thing that's required. Everything else is managed at the backend. Small insight. I'll just take 2 minutes to describe this. So we saw this window, right? Soft phone. So when I mentioned that Connect uses all these endpoints at the backend, it implements all these connectivity establishments in terms of WebSocket. So for example, your signaling server, your soft phone. So when I take calls, I can still take it from my laptop. So you have the soft phone. This uses load balancer. The media port, 3478. Then you can also have client-side metrics. So this one, where you can measure the productivity of the agents, and API. So all these UIs are rendered via API. So these are the API endpoints. If you're using chat, we have something called as the persistent connection service, which works over WebSocket port 443. So again, these are the endpoints that again Connect manages internally at the backend. So given that all these are managed, the problem of scalability is, 80% remote, except for the right sizing of the instances. So how many calls do I need to have? How many agents will be a part of my contact center? How many, routing profiles would be there? So all these things are the only thing, that customers or, end users need to manage. But everything else is taken care of. And all this with just your browser. Yeah, that is all from my end. Please let me know if you have any questions.
Thanks, Abhilash. Thanks. The floor is open for questions. Oh, sorry.
Thank you so much, Abhilash. This was really refreshing topic. I think it's kind of new as well. Probably a naive question. So let's say that like we are in charge of a service and we have customer internally and we want to integrate into our Slack channel that, some Slack bot will understand the context of the question and answer accordingly, right? Do you have sort of like from this, do you have same sort of like integration from Amazon Contact Center, or like it's a package of its own, it's a service of its own?
No, even if there isn't a direct integration, you can leverage APIs. For example, you have, that is where the serverless component comes into picture, what I mentioned as Lambda. So for example, if we look at this flow, we have something called as invoke Lambda function. So you can, provide what Lambda function you need to configure. So that Lambda function can make calls to your Slack APIs. And that will be able to, your Lambda function should have credentials to access it. It should have right permissions to go into that workspace. But after that, you will be able to get all the personalized stuff. Only thing is, if you're doing that, you need to have your own custom UI. So the one that we see here, this one, or even this one, these are managed UI. But there are separate GitHub repos where you can replicate this entire software in your own custom application. Let's say you have your own company, you want to embed this as a widget in your chatbot. You can leverage those SDKs and GitHub repos to configure it as per your requirements. So there you have this Lambda function which will make the calls. Then Lambda function can populate that web page, simple, web development aspect. So that way you can still get personalized, customer queries. But the ones that we currently have an integration is for Zendesk, Salesforce, ServiceNow. So you have something called as Wisdom or customer profiles in Amazon Connect. So as soon as you get the number, you'll get the entire history. What were the last recent calls? Because some of them use multiple CRM applications, right? It is not possible for them to migrate everything within Amazon Connect. So you can just have connectors to have that populated. So if you're going through your custom implementation, I would say serverless option is the best bet.
Okay. Thank you so much.
No problem.
Hey, Abhilash. So the question is about what are the multilingual supports, like, for example, for sentiment detection, right?
Yeah.
Say if the customer speaks in a language other than English, so will we be able to detect like sentiment and abuses, basically, like say, that's most common in this particular field, right? So how do you handle abuses? Like, can we flag abuses, and also the transcripts?
Okay.
Transcripts, do we get transcripts translated? Say if a customer talks in some non-English language, will we get transcripts for that as well?
Yes. So for example, okay, let me just show you this. So this one is again, as I mentioned, to enable recording or something, you don't have to do any configurations. Connect integrates internally with Comprehend. So you have a set recording block. In Connect, lingo, we call everything as a block here, just drag and drop. So you have, multiple, what we say, options, like you can record the agent and the customer, and then you can enable contact lens. So contact lens is the feature that adds intelligence into that conversation, like detects the sentiment. So you have two options here again. You can do it in near real time. As and when the customer is talking, you can detect it. Or you can do a post-call analytics. Post-call analytics usually takes 20 to 25 minutes to generate the transcript, but that also depends on the duration of the call. If the call goes longer, it would take longer. And coming to your part, language. So these are the languages and the dialects that we currently support. So even if you take English, there are multiple accents like, Indian, Spanish, Irish, Scotland, Wales, so on. So we, multiple language supports continue to come, but currently these are the lingos that Connect would be able to detect. Does that answer your question? Thank you.
Hey, hi. I had two questions in mind, and I seem they are a bit interlinked. The first one being, let's say you showed that a simple chart or flow chart of how the things work at a typical center. You took an example, right? So at the same time, what I feel like is that how do you ensure that you have a lot of features there, but it still remains a bit simplistic?
Okay, that would depend on the use case. So for example, in terms of simplicity, you can make it very simple. For example, you can remove these two blocks if you don't want to log any data. But most of the organizations have audit and compliance requirements. So you need to, have all these blocks. So when you talk about simplicity, it is very subjective. So you can have a bare minimum contact flow. Like, for example, this is something that we call play prompt. A similar thing would be like a simple printf statement, or a print statement that we have in programming languages. It will play the welcome message. So if you don't want your contact center to be more interactive, you can remove these blocks as well. So if there is a certain requirement, it would always be there. If you want all these features to be there, there will be blocks for sure. But yeah, once you construct it, it becomes simpler. Again, to answer directly to your question, there isn't a requirement, but if you want to remove all those functionalities like logging and all those, it would become a little more simpler. Or you can break this into multiple flows. For example, this is just one flow. You can have multiple flows, like small flows. And these are called flows which have limitations, like they can't exceed more than 1 MB. You can download these flows and import as well. They are JSON files at the backend. So you can still download it and import it. So this flow is pretty simple. If you see, the functionality is very less. So compared to that, this is not going to have any this will have intelligence, but it's just going to get press 1 for car related queries, press 2 for train booking related queries, press 3 for flight. So the call comes here. Once the user presses their option, the calls would get routed. So this is a simplistic flow. It depends on your use case.
Yeah, I do understand that that you are allowing the users to customize it in the way they want.
Yes.
What I want to understand is that how do you as a company ensure that your product, when the customers use it, they use it quite wisely? As an engineer, how do you advise them? Or let's say, for instance, you have your AI also in place. So how do you ensure that they don't overuse it? As in, they can overpopulate the data. They can have a lot of rich data and analysis of that, but all of that might not be useful. As I see, there's always a trade-off, right? So how do you ensure that?
So first things is, we don't have access to our customer data, so we don't monitor it. So unless and until a customer says that there's some data bottleneck or something, we would never know, because these are PI related data, so we don't track it. So to be honest, as far as my observation goes, we haven't come across such a scenario for your data storage related aspect, right? Okay. So log whatever is required. Don't log everything. So first thing is log whatever is required. And if you're performing, analysis, there are two options. You can either perform it real time or post call analytics as well. So basis the severity or, the customer's query or, the business use case that you have, perform analytics again on whatever data is required. So, and one more thing apart from this is, when you're recording calls, all these would go into the S3 bucket that you configure. Again, record whatever is required. If you ask me the best practices, what we usually do is we get on a conversation with the customers to understand what their business use case is, and then we recommend. We don't have a standardized template. Okay, this scenario you record all this scenario you don't do all this. So that we may not be able to set a baseline. It depends on a case-to-case basis.
Hey, I have a question. So, I mean, nowadays the trend is changing. People usually don't call, they tweet, right? So for example, if they have a bad experience with one product, they usually tweet. So do you guys also do tweet analysis? Like if someone is basically having a problem, instead of they calling you, I mean, can this platform detect if someone is having a problem and they're tweeting about, for example, this problem and dot, instead of calling, right? I mean, that's a trend which is happening at the moment, right?
Yeah, we do. So there are scenarios where if, for example, one scenario is this block, it shouldn't be cyclic. For example, okay, let me show something like this. So for example, if I have a block or a logic like this will run in an infinite loop. So this is something that is not recommended. So this is one such scenario. So if we have customers who are using these configurations, we reach out to them and tell, hey, this is something that you shouldn't be doing. We'll have to configure this, in a better way. So this is one of the scenarios where we reach out. Again, if they are getting throttle for a lot of calls. Let's say that their active call capacity is 100, but they are constantly, getting like 150, 160 calls. That would mean like 50 or 60 calls will never reach the infrastructure in the first place. I mean, it would reach the infrastructure, but it would never go to the agent. I'm sorry, it would reach the infrastructure. It would never go to the agent. So those may be other scenarios when customer traffic is high. We get in touch with them to tell this is something that is kind of hampering. So we need to take a look into it.
Yeah. So the problem, the follow-up question is like a false positive tweet can happen, right? I may complain for something which is not actually a problem, right? And lots of people can do that. So how do you detect those false positive things, right? I mean, you'll not end up calling everyone who is tweeting things, right?
Yeah.
So how does that analysis works, and how does you make sure that for example, your team or other your colleagues may contact only those people who are having genuine problems, but not actually just tweeting for fun?
Yeah, in that case, like you said, it is not possible to reach out to every customer for every small problems. It is based on the priority, because AWS runs on a distributed architecture environment. If there are certain components that are affecting one of these internal components, for example, more calls or bad practices, then more calls would start coming in, the signaling server would get affected. That may in turn impact the calls of other agents. So these are the scenarios that we prioritize. But in general, for small issues that may be specific to the customer, that is something, would always take a step back compared to the larger scale impact.
Thank you.
Thanks. If anyone has any question, reach out to Abhilash. Abhilash will be here on the floor only. Thanks, Abhilash. Thanks a lot for the great talk. So now we have our next speaker, Mithun, who will be speaking about detailed how did he reach out to improvements. Let me.
Hello. You can hear me, right? Thanks. So, Anil, how much time do I have? 30 or 45 minutes?
We have total 45 minutes, 35-minute talk and 50 minutes.
Okay.
But again, it depends on the audience. If you guys want to extend by 5 minutes, we are okay with that.
Okay, it's not that interesting a talk, and plus it's the last talk of the day, so I won't hold people up. So welcome everyone. So today this talk will probably be a little different. This is more of a indie SaaS product, very small team, but we scale out to, thousands and thousands of users. Okay, no, I have the next slide, which talks a lot about me. So my name is Mithun Shanbag. So I basically work as an independent software consultant, freelance developer. So I primarily spend my time around Microsoft-centric technologies, Azure, Angular, .NET, TypeScript. So I offer developer services, architect services, CTO services, whatever people pay me for. Most of my time is spent building micro SaaS apps. So small paid software built by teams of like 1 or 2 people. So some people in this room might know me as the author of CloudSkew, which is like a diagramming tool. So if you draw a whole lot of AWS architectures or GCP or Kubernetes diagrams, many people use this tool. Today's talk is around the quiz application, quiz.confirm.com, which is part of a larger, the quiz application is a part of a larger conference management application, and I'll get into that. And plus whatever my clients need me to develop, I'm under NDA, so I can't talk about most of those things. Prior to this, I used to work at Microsoft. I was there for about 12 odd years. Worked on Windows Server, Common Language Runtime, Visual Studio, Azure Cloud. So I had a pretty much of a journeyman career there. And that's my Twitter handle. I'm very active on Twitter. So feel free to reach out to me, either on Twitter or on LinkedIn. Okay. All right. So the app. Late last year, I worked for a couple of months on this application. So this is mainly the scenario is like this. Have people here played Kahoot? Like it's like between a conference or a meetup talk during the break, you play this quiz. 15 odd questions, and then whoever tops gets some prizes. The same theme, except this was meant for like remote first. So it's not like audience in a room. Although audiences in a room can play it, but it was more for a distributed global tournament. So we had tournaments with 8 to 10 quizzes, and each quiz had like 10 to 15 questions. It's completely, and somebody sponsors the quiz. So one of our main sponsors was Microsoft. And now we have a couple of other companies that have these quizzes either as a marketing exercise or as a hiring event. Whoever finishes in the top 5 of the tournament gets a chance to hire with the interview for that company. So this is what the quiz experience looks like. So this is the landing page. So you have a whole bunch of quizzes, and quizzes are sort of like grouped by tournaments. Okay. And generally, when you top the tournament, you win something like an Xbox or an Apple Watch, depending upon what the sponsor wants to give. And you can see all these things like, how many people have registered, blah, blah. So it's like a plain vanilla landing page. There's nothing special here. So you can go to the landing page. You can register for the quiz. You can view if it's a previous quiz, you can view the leaderboard, blah, blah. Nothing fancy here. Okay. Next is the quiz app itself, the quiz room. So here, this is every question has 4 to 6 options. It's like a Kaun Banega Crorepati style thing. You have to lock an answer, and that becomes your final answer. So looks something like this. So on the top right, you have a YouTube widget. That is where the quiz admin can use to stream things. There is a live leaderboard. There is a YouTube chat widget as well. And plus there's a timer running down for each question. So right now it's 19, 18 seconds, and you have to select an option. And once you select it, it's locked. And then at the end of the timer, we show the statistics. So here the user selected some option, I think second option. And as soon as the timer runs out, the statistics will be shown. Okay, so selected the wrong answer, and then their position in the leaderboard will fall or rise depending on how they answered. So that's the MC playing it through the YouTube Live widget. All right, so this is the app, okay? So we've opened this platform for folks to create their own tournaments, create their own quizzes, so people can play it at any time. We've been, people playing it at 2 in the morning, in different parts of the world. So, but then we also have our sponsored tournaments that run on every Wednesday evenings, Thursday evenings, and Friday evenings. And that is when we get peak traffic. So if there's a Microsoft sponsored quiz, we generally see, like 20, 30,000 people playing at one time. So what does our workload look like? Okay. So this is my API running on Azure Functions, which is for folks who are not familiar with Azure, this is like Lambda, AWS Lambda. And you can see that when a quiz is not happening, which is, most of the times, there's just a landing page activity. You're going to the landing page, you're, just looking up when is the next quiz coming up, you're registering, but it's almost flat, nothing. But then during the Thursdays, Fridays, evenings, when 5 o'clock, when there's a quiz, you get like a 5,000x burst in traffic, 5,000 to 50,000x burst in traffic. So that's the workload. It's like very spiky in nature. When there's a quiz in play, we get huge traffic. Otherwise, it flatlines. Okay, so you can probably guess where this is headed next. So this is the API. This is my DB characteristics. It's exactly the same, right? When there's a quiz, we have load on the DB. Otherwise, nothing. And same with the WebSocket. So the quiz application receives questions in an encrypted manner over WebSockets. So same again, WebSocket activity. When there is quiz, there's WebSocket activity. So now, having looked at this, it's spiky workload, which means I shouldn't be reserving capacity, compute or storage or otherwise. I should just go with serverless. And this is where we are at. It's entirely serverless. It's entirely pay as you go, because there's no point reserving capacity 365 days a year when it's only played for 15, 20 minutes on a Thursday and Friday evening. So guiding principles, obviously serverless. Other thing is like, this is a team of 1.5 people, one full-time developer and one part-time developer. So we decided not to invest too heavily in infrastructure. We'll go with whatever Azure provides. Plus we had free Azure credits. So made that decision very simple for us. So entirely platform as a service, right? So if there is a managed service offering, we'll use that rather than managing our own, say, Kubernetes cluster or on-prem infra. So we don't have any on-prem infra. We don't have any Kubernetes cluster. Whatever we have is entirely either platform as a service, which is like a managed SQL Server or a managed Cosmos DB, or it is entirely serverless. So yeah. So we use the microservices pattern everywhere. So essentially break everything down into its own component services with its own databases, centralized key value store, self bootstrapping applications, blah, blah, the whole 12-factor app thing. So there's this great book by Sam Newman you can read up. If you don't have the time to read, just go to that 12-factor app website by Heroku, and that sort of like summarizes the book. And there is this great link, which, I don't want to click on it. And can I click on that link and it'll open up a new page? So, okay. So if you're working with Azure, this is a page you should keep coming back to. So we essentially use pretty much every single Azure service under the sun. And during the course of building this app, I sort of realized what are the scalability limits, quotas on every single service. So per subscription, what is the quota? Per account, what is the quota? What is the ingress limit on the storage account? So blah, 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 blah. Just, name a service, I've probably either hit the limit or planned for it. Okay, so this is a good thing to look at before you start doing your architecture. Now, how do I get back to Okay, thank you. Okay, full screen. Thank you. Okay, so this is what the architecture looks like. And, probably looks busy and over-architected, but there's a reason why every single piece is there. And that's my next set of slides. I'm going to walk through every single block. Think of it like, playing Lego. You have a whole bunch of Lego, you just slot them together and, spin out an app. That's exactly what this feels like. All right, so front end, back end, DevOps, everything, I'll talk about it. So this game is played in browser. We don't have a Android or iOS app yet. It's in development. But for all intents and purposes, on your laptop, desktop, mobile, you would play it in browser. Okay. So I mentioned that this is entirely built on Azure, but this quiz application is also a child application in a larger family of conference management apps. That conference management app is entirely hosted on AWS. Then Microsoft came along and said, we want you to also create a quiz component, and here are free Azure credits. So we had to somehow retrofit Azure into this larger AWS thing. So that's why the DNS management of the parent conference app is on Route 53 in AWS. So all the CNAME records, text records are all in there. So basically we have some DNS entries, basically CNAME records that point to our Azure CDN endpoint, right? So the next thing is this Azure CDN endpoint. So everything, all the static content that you saw, all the images, all the JavaScript files, CSS, HTML, all the static content, it gets served out of this Azure CDN. Okay. CDN, obviously the benefits there are, caching and compression, you get it, obviously. Then there's also managed TLS search and a whole bunch of URL rewriting that we do. Okay. So I have a slide that talks about that. Origin is always storage account. So we authored the apps as React.js application. And so they are served out of a storage account. So this is like serving your application out of a S3 bucket. So that's our origin. Okay. Now, all of this gets, when you hit that endpoint, quiz.confirm.com, you traverse through this DNS, goes to the CDN endpoint, goes to the origin, and then everything gets loaded in the user's browser. So this part is straightforward. So once that's, then the app takes over. And all the, all the requests that the app generates, there are two sets of apps, one for the quiz player and one for the quiz administrator. So all the requests go to this API gateway, or what's called in Azure as API management. So API gateway is where all you centralize all your policies, your rate limiting, CORS, JWT validation, your Redis caching, all those policies are aggregated at the gateway level. So the very first thing it does is like JWT validation. So we have to fetch some things like, the audience authority for whom the JWT was generated. So that is fetched from Key Vault, so secure key value store. There are other things that we store in the Key Vault, like all the connection strings, all the passwords and stuff, all go into the Key Vault. So this is an audited secure key value store. Similar to what I think is KMS in AWS, I think. Okay, so the gateway fetches that, and then it has to talk to Cognito. Now, why Cognito and not Azure Active Directory? This is because the user pool in Cognito is also the user pool of the parent conference management app. So we are just reusing the user pool from Cognito. So Cognito exposes the OpenID server, OpenID endpoint URL that we talk to and do the JWT authentication against. Okay, so then Cognito says, yep, you're good. The JWT has been validated, and now the call can resume. So for some things that are very hard to compute, or something that is like looked up very frequently, like for example, during the quizzes in progress, the leaderboard, we have to cache that. So the caching happens with Azure Redis. So that's just hanging off of the gateway. So the gateway says that, yeah, this is a frequently used API. Let me just go into the Redis cache and fetch that out. For stuff that is not cached, we send it to the Azure function, which is your Lambda. So all the incoming requests are routed there, and they're not executed immediately. They are queued in a service bus. Now, this is like Kafka or SQS in AWS. So we just pull it. So this is a pattern called queue-based load leveling. So there's a burst of requests coming in. Now, remember, you have 30, 40, 50,000 players playing at the same time. They're submitting their answers. We are not going to be evaluating all of them in one burst. We queue them up, and then we dequeue them in batches. So that way the load on the server stays predictable. So that's a pattern called queue-based load leveling. Just pull up all the incoming requests and then dequeue them in batches which you can handle. So the batch size has to be such that it doesn't overwhelm or overload the server as well. So then we dequeue that, and then we go operate on our hammer our DB. So it's Cosmos DB, which is like a hosted MongoDB, if you will. It's a document store. Everything is stored as JSON documents. So all the user answers go in there. All the evaluations happen in there. So user submits their answer, goes into the DB. Now we have triggers on the DB that monitors. Hey, user answer came in. Now maybe it's time to update the quiz leaderboard. Now it's time to update the question leaderboard. and also parallelly update the tournaments leaderboard. All those things happen in parallel, right? In real time. So we have triggers set on that. And the trigger wakes up this quiz engine, and the quiz engine starts evaluating. So let's say you submitted an answer right now, and maybe you submitted a wrong answer. So your position in the, for that question has to be scored. Your position in the overall quiz will go down and the tournament will go down. So that happens in real time through that trigger. Then once the evaluation has happened, it has to be dispatched back to the user. Now we don't do it through the REST endpoint. We send it through a secure channel using web pub/sub. Now web pub/sub really means it's a fancy word for a managed WebSocket server. Okay, web pub/sub means something different in Google. Here it means WebSocket. So so we dispatch that to the web pub/sub server, and web pub/sub server is responsible for maintaining the resilient connections with the client, retries, all that, and throttling, rate limiting, all that is handled by the web pub/sub server. So as soon as the user, when the timer ran down and you saw that the user, you saw some statistics, all of that is dispatched to the through the WebSockets. And that's a secure channel. We AES encrypt all our data and it gets sent back to the user. So that's our round trip. So user to front end gets loaded, API gateway, and then back to the functions which gets queued, dequeued again to the Cosmos DB, and back to the functions on triggers, and then evaluations get sent via WebSocket. Okay, that was a tour of the application. Okay. There are other things like monitoring, metrics, alerting, dashboard, all of that is there, and we completely rely on Azure Monitor for that. Like we are not using any open source or third-party packages there. We have free credits, so we just use what's available, and it works pretty well. And for DevOps, we have Azure repos and Azure pipelines, CI/CD pipelines. So every time there is a commit into the main branch, it automatically deploys both the front end and back end code to the test environment. There's also production environment, which is a replica of the test, but we don't automatically push it. We manually push it to prod whenever we feel like it. Okay, that was the tour. Okay, now how much time do I have? Okay, perfect. I can talk about all my scaling challenges right now. I need water. All right, so it's all these Lego pieces, the CDN, DNS, service bus, Cosmos DB. Now let's look at each individual block and what scaling problems does it, does it have? Like remember that pages with quotas and stuff like that, we'll be hitting every single limit and scalability limit and quota along the way. So we'd actually planned for that. So this is just, let's go through each block one at a time. This is just mobile, the application getting loaded in the mobile. There is no scalability challenge here, straightforward. DNS Route 53 handles it perfectly, no challenges there. CDN, yeah, so some interesting thing, right? So we use the Microsoft Classic, today morning we talked about front door. This is not that. We are using the cheaper version because, we use front door, we'll exhaust all our credits. So we use the Microsoft Classic. So Classic comes with the challenge there, right? So if the file size is greater than 8 MB, it's no longer compressed and cached. So to get around that, what we have to do is we have to break it down into chunks. So in React, this thing is called chunking. In Azure, you call it lazy loaded modules. You basically split the modules. 8 MB. Why are you paying for that? Good to know. Good to know. Okay, so essentially, here's what's happening, right? So you see that I don't know if this is visible at the back, but every of those files is broken down into chunks. And we ensure that the size of each chunk is less than 8 MB. So that way it is cached and compressed. we use the rewriting rules to set the cache control header. Now, this is a scenario where, people on their mobile are just, swiping down, that refreshes the page. And we don't want to fetch all the static images all over again. So we want to put that cache control header in the response so that the browser caches it. So if you set it to something like, max age 3600, which will cache it for 1 hour, which is more than enough for the quiz. So we use the rules engine in the CDN to set that cache control header. So now any user accidentally presses refresh, the page is loaded with a latency of 0 milliseconds. Okay. So you can see that there is no network transfer. It's all loaded from cache. Latency is 0 milliseconds. That was one optimization. And after that, we were good. Storage accounts, no problem. We were well under the ingress and egress limits. And even if you exceed those, you just get billed a little extra. There is no scalability challenge there. Okay, you don't get throttled there. API management. Okay. This was interesting here. So cores. So if you have cores, you have the allowed origins and allowed headers, all those set on your APIs, the browser will send a pre-flight request, an options request, basically to check whether the server is capable of handling the request that the browser wants. So it's best to cache those pre-flight requests, else the browser will be sending too many of those. So what we do at the gateway level is whenever we detect that it is a pre-flight request that's coming in, we cache the response, and for a duration of 5 minutes, we send out the cached response. So we set this max age as 300, which is 300 seconds, 5 minutes. And anytime the browser raises that options request again in that page cycle, you are getting a cached response back. So that greatly speeds up things. So generally the pre-flight request takes around 300 to 400 milliseconds to execute. We sort of save on that by serving out the cache requests. Next, okay, so this is something we learned the hard way. Actually, we learned everything the hard way. We had logging turned on, 100% sampling. So every single request that was coming in was getting logged in Azure Monitor. So, and at that burst of traffic, that was actually slowing down the request. So we turned it from 100 to 95 or something, and that eased up pressure a bit. So we decided, okay, all these requests are going to be the same. There's no point, set the sampling to like 90 or 95. That's more than enough. You'll lose some of the logging samples, but that's okay. It's a 15-minute quiz. You don't care too much about that. It's not like, you are doing any payment transactions or anything. It's just a quiz. So after that, we were good. Key Vault, no challenges. Cognito, no challenges. Redis. Okay, so this got interesting here. So we want to make sure that the most expensive calls get, cached. So an example is if you're playing a quiz, while the timer is counting down, scores are not going to move, right? You're only going to update the leaderboard after the question is over. Although we are computing it in the back end, but you are only going to show it after the question is over. If you show it before the question is over, you give an unfair advantage to the people. So we want to cache it for the duration of the question, for that 30 seconds. So we decided to cache that. So we were caching it for a little bit longer. So we set the max age there on the Redis cache itself, Redis cache policy. And what happened as a result was our hit rates far exceeded our misses. Okay, so the first time you ask for the leaderboard, obviously it's going to be a cache miss, but after that everything is going to be loaded from the cache itself. So the hits started, exceeding, overwhelming. The misses started to become less, and as a result, our database load, or what we call the normalized RU consumption, started getting, instead of being a flat thing, which would peg the database, it started becoming a narrow spike. Earlier, it used to be flat like this, but then at a later point, it started getting narrower. So only on the cache miss, you are going to have that spike. Other than that, it's like smooth. So the goal was to reduce the number of spikes and as well as the duration of the spikes. So putting in that Redis cache greatly helped there. Web APIs. Now this is gonna go a little bit into Azure, so I'll try to skip past some things. So one of the things we do is we enable something called as a scale controller log. Now this is serverless like Lambda. As soon as the rate of incoming requests increases, it automatically horizontally scales out to multiple instances. So we wanted to make a note of how many instances are getting scaled, under what conditions they are getting triggered. So all of this is generally opaque unless you enable the scale controller logs in Azure Monitor. We did that. We started getting good insights from that. Then, warm-up trigger. Okay. So P99 latency. So most of our APIs, right, would return between in less than around half a second. That was the latency. But for some outliers, it was around 6.8 seconds. So why did we have these outliers? Turns out it's the data. So every time there's a new instance that gets horizontally auto-scaled out, it is a cold start. So, and if it has to fetch something from the DB, it has to reinitialize the DB connection all over again. So that handshaking with the DB causes that, latency. So stuff that a warm instance will return that call within 500 milliseconds. A cold one was taking around 6 seconds. So we started using something called as a warm-up trigger. So warm-up trigger, essentially what it does is it initializes the scaled out instance in a warmed up fashion. So it can't serve traffic until it's completely warmed up. So by the time it's available for you to serve requests, it's already pre-warmed. So this is what the latency looked like. So you had your API gateway, you had your function, and you had your database. Okay, so API to function was very little, but from the function to Cosmos DB, that long latency was the DB warm up. And once the DB got warmed up, you can see this small dot here, that's execution time. So that entire thing should have executed in less than half a second, ended up taking 6. So we had to eliminate B there. The B was now, once we moved to the warm-up trigger, everything got resolved. All right. Service bus. Now this is just queuing stuff. So we were queuing it, but then we were dequeuing it one by one. So we decided, this is not any good. We should dequeue it in batches. We dequeued it in a large batch of 10,000, and that started overwhelming the server. 10,000 concurrent writes is never a good idea. Can handle it, but so then we decided to scale down the batch size, and we were good. We also decided to scale out the number of auto-scaled instances on the receiver side. So you don't want 50 instances of the Lambda hitting your database. So we limited the scale out instances to 3 or 4. Cosmos DB. Cosmos DB. So Cosmos DB has this concept of containers, which folks who are using Mongo will be familiar. In Mongo, it's called collections. Here it's called containers. Containers are, they run disproportionately hot. Not all containers exhibit the same workload. So we had some containers that were like taking up most of the throughput. So we call them hot containers. So we identified the hot containers and we sort of worked our way around it, right? So we decided to break the workload down. Then some other Azureisms, we raise the throughput too high and then it retains memory, and then you can't raise the throughput back to its original level. So, I mean, I don't want to get into it, but there's this math on ceilings and floors. We realized it the hard way, then we had to do a DB migration after that. So, okay. Again, Azureisms, I'll skip this. Okay, and other thing is like for the large leaderboards, right? We had documents like 600, 800 MB. This is just, 20,000 players. Here is the questions, here's the answer they chose. Here's their ranking. It's an array. why do we need to index it? So we dropped that from the index and our write commits became faster. And then we were good. What else is there called? Okay, so we have triggers. Triggers increases the the throughput consumption. So we were now pegged at some level. So we decided to decrease the frequency of polling, and then that brought the throughput consumption down. So essentially in Azure, it's called a feed poll delay. Triggers also add scale out pressure. So your trigger causes your throughput to rise. As the throughput rises, the infrastructure feels, hey, this is way too much throughput for one instance. Let me spawn out multiple instances. Now, each of those multiple instances also have triggers, and then that goes into like a death spiral. So we have to do something about that as well. So we have to limit the number of scaled out instances. And also some things like, not do full partition scans, just do point queries where you specify the partition key and the row key. And this web pub/sub thing, this WebSocket thing, this is my personal hell. I've still not been able to figure this thing out. It's a fairly new offering from Azure. So it has two components. There's a fixed price component and there is a variable price component. So let's say there is something called as a scale unit. Each scale unit will serve 1,000 participants. So 1,000 participants gets WebSocket connection. That's the fixed price component. You move to 2 scale units, price doubles. Straightforward math. But the messaging part, right? This is where you need a PhD in mathematics. So the size of the messages, the frequency with which you send it, the number of connections in a group. So all of these factors will ultimately determine the pricing. And for the life of me, I was not able to figure it out. So I've just left that as is. It's still on my plate. It's still not optimal, but I'll figure it out someday. And everything is AES, double AES encrypted and sent across to the players. There's still some optimization challenges there. I have to figure it out. DevOps, this is what my dashboard looks like. So every single Lego block on that thing, fires out metrics and we monitor everything, right? Like number of service bus, there's a number of dead lettered messages. For web pub/sub, the outbound traffic, the max number of connections. For the Cosmos DB, the normalized throughput. So we monitor everything. There is exceptions, errors, warnings that are happening in real time. We can monitor all of those. We now don't even monitor this. We just set alerts. So we have thresholds identified and we just set up alerts. So, if the throughput rises to 70% of its actual capacity, just raise an alert and have a ticket fired out. This is the application map. So it helps you identify after the quiz. This is like a post-mortem activity we do after every quiz. And that red thing is the hotspot. So the latency is higher than the threshold. So why is it higher? Then we do a deeper drill down. The front end and back end, both. And other things like, this latency maps and all those things are figurable. And DevOps pipelines. We have 2 environments, both for provisioning, we use Pulumi. So they're identical replicas of each other. The only difference is the key vault values are different. So in the prod key vault, you'll get the connection string to the prod database. In test, you'll get it to the test database. Other than that, they're identical. And every single commit to the main branch goes automatically into the testing environment. And then we promote some of the builds into production environment. All right, so that was it. Questions?
I have a question. So the first question is around the leaderboard. Leaderboard has been an interesting problem to solve.
Yes.
Because beat any sale in Flipkart or beat any player game anywhere, we always want to keep an eye. And considering you're talking about quiz where it can be more than 10K players sometimes.
Yeah, the max we've had is I think 32 or 33,000 players.
Yeah. So that how did you solve that problem to 32K to 33K players at the same time in the leaderboard fresh always?
Yeah, so all that happens in the quiz engine. So we can't unfortunately do a distributed calculation there. So you have to calculate every answer one at a time, because you answer something correctly. Now you rise to, let's say, position 68 out of 1,000. Then he answers correctly, but in a lesser amount of time. Now he rises and your position falls. So it has to be done serially, as far as I know. So yeah, it's slow, it's asynchronous in nature, but that is why you will sometimes see that, as soon as the timer runs down, you get the leaderboard updates in real time, but the leaderboard updates will still continue for a few milliseconds after that. I don't know if I answered the question, but yeah. Are you trying to hack the quiz or something? Yeah. In real time, yes, it has been
a real time problem, and it's not. I'm not talking only about the case of e-commerce or quiz.
Yeah.
It's a bigger problem to solve. And I know that many e-commerce players or many game players, they're always trying to solve this problem only.
Yeah.
Because there's a one thing where real time they say, okay, now you reach to 10th position. If you will do this much, you will reach into this one even. Interestingly, CRAD also has that game. I hope somebody from CRAD can.
Yeah. So we have not only a right answer. You are not only scored on the correctness of your answer, but fastest fingers first. So if you answered correctly and then you answered correctly, you would still go above him on the leaderboard. So, so some of the metrics that we queue is the NQ time. Right? At what time was the answer enqueued on our server? You may have a slower network connection. So you will get penalized for it, unfortunately, because your answer comes later to our backend. So unfortunately, we can't be in control of that. We can only consider the question, the answer as arrived when it gets enqueued in our backend. So
for leaderboard, are you using your internal data structure, or you are using a sorted set of Redis, or?
Pretty sure it's the end of the day, it's some array.sort or something like that. It's not like, so I told you, right? The entire engineering team is like 1.5 people, and we also have to manage, like marketing and sales and all that stuff. So yeah, I'm pretty sure it ultimately comes down to array.sort. Yeah. Sorry, I don't have a highly scientific answer there.
So this is something same around leaderboard. So do you do this real time on every answer click, or? Yeah.
So as the answer comes in, it gets queued on the service bus. And then we dequeue them in batches, and we just run through the batch. And for every answer, whether it's right or wrong, how much time it took, we just update the leaderboard. And at the end of the batch, the leaderboard gets transmitted to the users. So that is like an interim leaderboard, right? That may get overridden by the next thing that comes in. So let me show you what I mean. So here, somewhere in our slide, now I don't know how to go back to the original slide, but how do I go back to the? No, like at the very beginning. I think it's like slide number 2 or 3 or something. It generally shows the panel here. Okay, now before. Okay, I think this one. Yeah, so here what happens, so here's what happens at the end when the timer runs out. You will get a leaderboard update, but that will immediately get flashed over by another update that comes in. So that's the next batch that is coming in. So if you watch it here, 8, 7, 6, 5, 4, and then you get the statistics and the leaderboard. Okay, and now you'll see these things will start moving in real time. So that's like another batch got computed, and it got, so that overlays on top of it. And then gets overlaid on top. So that thing will keep moving. So we generally expect that from the time the timer runs out, for the next 2 or 3 seconds, you will keep getting answers.
All right, that answers actually. So my next question is, you said you were using Redis, right? As your Redis. So what exactly, only for serving the leaderboard or doing something else? I mean, you said that API gateway connects to Redis.
Yeah. So some of the things like, let's say you want to, leaderboard is the main thing that we serve. Other stuff, let me see, from the API, it's been a while. Like some of the quiz details, like the like quiz registration times, like, you know, when is the quiz start and end time. So those things, details are not going to change much. So those things we serve out of that. But yeah, mainly it's around leaderboard. Yes.
Another question on the same thing, same line. So why don't you use CDN for serving directly instead of using Redis cache?
CDN is for front-end static assets. Redis is for the API. Redis is mainly for JSON data that we load from Cosmos DB. So we just preserve that in the cache. The CDN is for things like your JS files, HTML, CSS, some sound clips, images, SVG files, all those things.
So I'm not sure about, I mean, with Azure, how it works, but with AWS CloudFront, you can also cache JSON responses like API kind of thing.
I'm sure it's possible. Yeah, I didn't know any better. That's my answer.
Yeah, because it's just that egress cost and on it when it comes to API, right?
Free Azure credits. Why do I care?
Yeah,
that is basically my, you know, like if you ask me, like, why did I use React over TypeScript? It's like, I knew React. If you ask me, why did I choose this over that? I just knew it, or, you know, Azure gave us free credit. So that's my simple answer to most of the questions.
Cool. Thank you. That's, I mean, too much detail right now.
Yeah.
I had the same question, like why Redis but not CDN, right?
Redis can integrate with the API gateway. So API gateway, at API gateway level, you can set up XML policy, which says that incoming request based on the key, just load that from the Redis cache. You can't, as far as I remember, you can't do anything at the backend with the CDN. So, so one of the things is the route, the URL, route URL will contain things like the user ID and things like that. So those are easier to map at the Redis cache level than at the CDN level.
So once it's cached, right, it's JSON, right, and you are saying that you have a max age policy of 120 seconds, right?
Yeah.
Even you can cache that on the CDN for 120 seconds.
Correct.
And even that, if I mean, after 120 seconds, anyway, they will miss. It's going to go back to your Redis or whichever backend you are implementing, right? So that was the same question which I had, but
yeah. So we did look at CDN as a place where the JSON leaderboard can be cached, but I couldn't find a way to easily integrate that with the API gateway. So that has to be returned through the API gateway. So CDN is mostly for front-end assets, Redis for back-end assets. Now, if you can show me a way where, you know, we can serve that same thing through the CDN and have it returned out of the API gateway, I'm more than happy to switch over to the
API gateway can be your origin. Right? So you can, I mean, you can have your CDN contacting API gateway, but again, as I mentioned, they don't have CDN to origin signing.
Yes.
So once that get implemented, then you can implement something like signing things so that you can have your JWT validations.
Yeah,
and get it served from there. Yeah,
good point.
Yeah, so I not a question but a suggestion. So you told about that you are doing batches. You are breaking down into batches, right? At client side. Now byte range coming into the support, probably you can ask that thing from CDN to do that instead of writing your own logic to implement that batching thing, right?
No, the batching thing is very specifically around service bus, right? So
no. So you told you have a bigger content, you break down into pieces.
Oh, that's the chunking on the React application.
Right.
So for what happens is, even with minification enabled, sometimes the chunk sizes go over 8 MB. So we are forced to, without chunking, it'll go over 8 MB, but we are forced to break that down into chunks and serve out those chunks. Else it doesn't get cached and broadly compressed. So now with the whole byte stream thing, I will have to look at that offering. Now I know it's only in front door. It's not in the classic CDN.
Yeah, in front door.
Okay. Well, we'll have that chat. But it's a good point. It's a good point.
Cool, cool. You guys, you folks can also
One more
we'll be here for another 40 minutes, so no worries.
I think there's one more question here.
Hey, Mithun, that was a very good topic. Topic. So again, on the same topic, Redis gateway. So how do you decide when to evict the cache? Like, you said about 120 seconds.
Yeah.
That would not work all the time, right? Because there will be some update based on that you would want to evict the cache. Then
No, so one of the things is like, see, the leaderboard comes in two fashions. One is if you're inside the quiz room like this, you are getting it in real time through the WebSocket. Okay, so there is no API or caching involved here. You're actually looking at the real thing. But if you're on the landing page, when the quiz is in progress and you're refreshing that, at that point you get served over the cache. So when the quiz is in progress, we really want to focus on the quiz activity and not on this thing. So let us serve it cached. 120 seconds is something we came at.
maybe it serves the particular use case, maybe.
So actually there are some nuances. In our telemetry, we recognize that some people were cheating. And I can go into a whole this thing, but essentially what happens is people were playing from multiple accounts. So from one account, you answer a question, and from the other account, so you get a real-time update here, whether you answered correctly or wrongly. So let's say it recognizes it as a wrong answer. From the other one, you do it correctly. So that was one of the disadvantages of doing a real-time update. So we held off on real-time updates until the timer expired. But then people would go to the quiz page and load the leaderboard live from there. So which is why we decided to cache that. Here we are holding off until the timer expires. There we cache it for 120 seconds from the time the question starts.
Yeah.
So yeah, all these are, like, what do you call, like, most of our population is like students who are playing it. Way too many time, way too much time on their hands. Yeah. So we have like people, from the same IP address, there are like 20, 30 accounts sending answers. So yeah, we had to do something about that.
Any more questions?
Thanks, everyone. Thank you.
Thanks everyone. With this last presentation, we'll call for the end of Meetup. Devanshu? I think for those who don't know Devanshu is the founding member or founder of LSP. He is the one who brought all of us here.
Thanks, Anil. So I think it's a little bit overstatement though. The better statement would have been there was a feeling amongst few like-minded folks to get into this kind of a forum. And that's what brought us together. The only part which folks like me and Anshu played, which I can say that, yeah, this was our arrogance, our stickiness to keep this live. So that's what probably kept us running through this 10 years. Within that, we had a bad 2 years pandemic when Anshu innovated that we should go in Zoom and stuff and start doing virtual ones also. Otherwise, we were almost like dead by the end of 2019 when we decided to bounce back. So thanks, Anshu, for all that doing in between. A community is all because of you guys. It's not like few of us who at times reach out to different people and request for hosting us. Community is mostly, it's all people. We are nearly 2,700 now. Okay. And despite using any of the catchy terms like DevOps SRE in our community name. It is still old-fashioned production engineering, and we haven't changed it. Okay. Okay. So I have seen communities which has 8,000 people, but they generally got vanished pretty fast. So we existed. Thanks for all your support and stickiness towards it. And we are getting more traction post-COVID. And hopefully our greener days are ahead. It was not in the past. So, and for this particular event, Anil, Vikas, Anshu, whole of the Grab team guys sitting up there did a great job. This is a nice ambience. And after a very, very long time, we got space, I mean, all taken away. We usually close our registrations at 200. So it was all taken away. So I was really surprised, a little bit tension as well, because we generally prepare for X amount of people to, which is overshooted today. We expected roughly around 60, 70 people to turn up. We had around 85 plus 20 odd folks on the live stream. So it's a great participation, and thanks for to all of you to coming on a Saturday. It's not a regular work day that we set out for office and then come to Meetup, because managers knows they're gaining knowledge. So it's not a rest allowed and stuff. So it's a holiday. Your family knows that, okay, my share goes. So, okay, fine. We are ready for giving up one such share once in a quarter. So thanks everyone for coming. Have a nice evening ahead. Thank you very much.
Thanks, everyone. Thanks for your time. So tea and snacks are ready, please. And the folks who want to ask questions, networking can continue here. Thank you. Once you want to click a group photo, that will be a great thing. So I'll request everyone to come here near the dais. So